Welcome to today's lecture. So today we will apply what we have learned about convex sets in finite dimensional vector spaces. We will finally apply it to one of the main topics of the series of lectures, namely to the theory of non-negative polynomials. So we are in section 7.5 of our lecture notes. Okay, so and we start with some really easy things. So what is actually a ternary quartic? So it's a very special case of polynomials. So a ternary quartic is a 4 form or also quartic form, C2, 3, 4, in 3 variables. So a ternary refers to a number of variables, right? And quartic refers to a if it's not a 0 form, when it's a homogeneous polynomial of degree 4. So it could be a 0 polynomial, or it could be a homogeneous polynomial of degree 4 in 3 variables. So quartic form we had defined within 2, 3, 4. So let's see. So I mean not quartic form, but quartic, or term quartic. We had defined it in 2, 3, 4. Yes, so that was with terminology, right? Polynomials of degree at most 1 are called constant, of degree at most 2 are called linear, quadratic for degree at most 2, cubic for degree at most 3, quartic for degree at most 4, quintic, etc. Here I'm speaking about homogeneous polynomials, so either they are a 0 polynomial or they are of degree exactly 4. In fact, each monomial is of degree 4. Okay. So when comes a really easy lemma, so let K less than or equal be an ordered field, and G a symmetric matrix, some m by m symmetric matrix over K. When G is positive semi-definite, right? What does that mean? 2, 3, 1. What was positive semi-definite? That just means that x transpose mx is non-negative for all x in K to the n, right? One could also say that a quadratic form represented by this matrix is PSD, which in turn would mean that this quadratic form is non-negative on K to the n. So this is the case actually. So actually, when one tests with non-negativity, one can exclude without any problems the vectors, those vectors, one of whose components is 0, right? So I can restrict to vectors all of whose components are non-zero, so they are in the multiplicative group of K, which is K without 0, right? Okay, that really doesn't seem surprising. So if K is the real numbers, then it's just an completely obvious continuity argument. If K is a real closed field, then now we have actually a topology on R, so you could also do it with a continuity argument, but another way would be to do it by Tarski's principle, since you know that it's true over reals. You can easily, with Tarski's principle, conclude that it's true over each real closed field. Yeah, but here it's a bit different, because we have here K is an ordered field, and this positive semi-definiteness is checked only over the ordered field 2, 3, 1, right? So it's actually not clear, at least not to me, at least not immediately, how you would actually reduce this to the case of real closed fields. And in the case of an arbitrary ordered field, one could probably also argue with some continuity argument, but in fact we did not even introduce a topology in this case on K. One could, of course, but when one would have to think about why things are continuous and so on. But okay, so I just give an easy ad hoc argument, right? So this is really a not in no way surprising this lemma. So let's just prove it with an ad hoc argument. So suppose X transpose Gx is non-negative for all x, for all vectors x with all of whose components are non-zero. Now let Z be a vector which might possibly have 0 components. We have to show that this is still non-zero, right? And I do here a little trick. So instead of Z, I look at all Z plus lambda y, right? Where y is arbitrary without 0 coefficients. So that's a vector without 0 coefficients. And so I have Z plus lambda y is, does also doesn't have 0 components, except for finitely many lambda, of course, right? That's really easy to show, right? For all but finitely many lambda, I have that Z plus lambda y has no non-zero component. Really easy to show, right? And since this has no non-zero component, I know that, this is here because G fulfilled the hypothesis of theorem, right? You could take this as our x now with Z plus lambda y. You know that this is non-negative. Now if you multiply that out, you get Z transpose G Z plus 2 lambda Y transpose G Z plus lambda squared Y transposed G Y. And you know that this is non-negative for all but finitely many lambda. Okay, so but when you consider this in lambda, right, that's actually parabola or something, right? So this is the constant part. This is the linear coefficient, right? And this is the quadratic coefficient. So, and since I know this is non-negative for all but finitely many lambda, it must be actually non-negative for all lambda. Why? Well, again, we need, I give an easy ad hoc argument. I could say that, look at this polynomial. It's a polynomial. And its leading coefficient is this, right? If a leading coefficient, and I want to show it with leading, the constant coefficient is this, right? Now I cannot just plug in lambda and say, okay, because I don't know if lambda, I know this only for all but finitely many lambda, and I don't know if I can really, if I know it already really for lambda equals 0, right? Because there are finitely many exceptions a priori. So what I do is, but that's a constant coefficient. If a constant coefficient actually determines the sign of a polynomial near 0, right? And therefore has to be non-negative because, it's not true that around 0 in a whole interval around 0 this quadratic polynomial is negative, right? Let's look at 153b. So 153b. Here. Okay, so you see the sign of a polynomial is it's the sign of in this way. So the smallest coefficient, which is non-vanishing actually, right? Which is non-zero, determines, in our case, alpha 1 would be 0 because we are looking actually at a constant coefficient, right? So the sign would be determined by, the sign of f of x is determined by the sign of this constant coefficient if it is non-zero. So both signs are the same if the absolute value of x is smaller than some positive number here, right? 1 over this maximum, if the absolute value of x is smaller than 1 over this maximum. Okay. Good. So that was really easy, maybe too easy, maybe I created too much confusion. So now comes already an important lemma. Let K be a Euclidean field. A Euclidean field, you remember, it's a field where the squares form an order, and then this is actually the unique order on it. So, of course, every real closed field is a Euclidean field. And suppose K is a Euclidean field and F is a 4-form. And so a homogeneous polynomial, all of whose monomials have degree 4, in 3 variables, which I call x, y, and z instead of x1, x2, x3. Suppose there are linearly independent v1, v2, v3 in k to the 3, such that f of v1 equals f of v2 equals f of v3 equals 0, right? So in some sense, this means that f has just 3 zeros, right? Because, f is homogeneous. So whenever you take a line through the origin, right, then if f vanishes just on one point of this line, which is different from the origin, when it will vanish, of course, on the whole line because of the homogeneity, right? And so, and so this means that in some sense I can, for those of you who know projective space, two-dimensional projective space consists of all lines through the origin. In a three-dimensional vector space, in our case, it's the k vector space k to the 3, right? So that these are actually representatives for one-dimensional subspaces they generate. So V1 generates a one-dimensional subspace V2 and V3. This can be seen as points in a projective space. And the fact that these are linearly independent, these lines can be seen as, these straight lines can be seen as points in a projective space. And that these vectors are linearly independent just means that these these 3 lines, first of all, are distinct, and or you could say that none of these 3 lines lies in the plane generated by the other 2 lines, right? Yes, so that's that means just that it's like it's a bit like saying that you have 3 zeros and they don't and they don't lie on a line in affine space. This would be the corresponding thing, right? It would be like 3 zeros that don't lie on one straight line. Here it's 3 projective zeros that don't lie in one affine plane. So they don't lie in a projective line. So for those of you who like projective geometry and so on, right? So basically it's 3 zeros that don't lie in a very special, which don't appear in a very special configuration. So roughly you could say I have 3 zeros, right? Okay, so it's certainly a very special 4 form. So it should have 3 zeros. And but when the following are equivalent, f is positive semi-definite, 2, 3, 1a, right? That just means that f is non-negative on k to the 3. Let's look at it again, 2, 3, 1. Yes, that just means that f is non-negative on k to the 3. F is the sum of squares of polynomials over k, and f is the sum of 3 squares of quadratic forms. Yes, I mean, actually, by what we know already or what we have seen, it is not astonishing that you can restrict here to quadratic forms. But in fact, we can restrict here to 3 terms in the sum. That's really some information that might be non-expected a priori. Okay. Yeah, and yeah, so in this very special situation, because you have these 3 zeros here, you have a very nice theorem, very good connection between, actually PSD equals the same as sums of squares. PSD equals SOS. People sometimes say SOS means sums of squares. Okay, so that's a very nice situation which we encountered already for univariate polynomials. For example, a univariate polynomial was non-negative, at least over a real closed field, was non-negative if and only if it was a sum of squares. For quadratic forms, we had a very nice theorem. Well, quadratic form is PSD if and only if it's a sum of squares of linear forms. That also worked over a Euclidean field, I think. And here we have another nice theorem, but in a very, very special situation, right? And actually later we will see that in the case where k is real closed, A and B are still equivalent even without this condition on the zeros here, on the existence of these zeros, right? So that will be our main goal actually for this section. The other main goal, of course, is trying to illustrate the usefulness of the notions which we have developed for convexity. And in fact, it's even true that A, B, and C continue to hold if k is real closed and even without this condition, right? But so even you have always a sum of 3 squares. But that's a theorem which was already proven by Hilbert in 1880, but the proof is not easy, and we don't do it here in this lecture notes. But here we get in some sense, we get it for free, that f is a sum of 3 squares for quadratic forms, so we have noted it here in this special case. So denote by E1, E2, E3 the standard basis, so the canonical basis vectors of k to the 3, of a k vector space k to the 3. And look at the following 3 by 3 matrix over k. So in the first column you put the vector v1 seen as a column vector, in the second you put v2, in the third you put v3. And so that's actually the matrix of base change, which so let me think, what does it do? So it takes coordinates it transforms coordinates with respect to the basis v1, v2, v3 of k to the 3 into coordinates of a standard basis, right? So it's a matrix of base change. And now we can take this 3 by 3 matrix over k and can multiply it also with a column vector consisting of these variables x, y, z, right? So that's now, I mean, A is a matrix over k, but in particular it's a matrix over the polynomial ring in 3 variables over k, right? And this is a column vector of length 3 over this polynomial ring in particular, and I can multiply a matrix over this polynomial ring with a vector over this polynomial ring if the size is alright, and that's here okay. So and then I plug it, so this gives another vector. This gives now a vector of 3 polynomials, yeah. In fact, these are 3 linear forms over k. Linear form in the sense of a polynomial. And I plug that, so I plug that in for the variables of f, right? So for x I plug in the first linear form, for y I plug in the second, and for z I plug in the third. That's what I mean by this, right? When g of e1, for example, is of course equal to f of v1, right? Which is 0, right? So, and in the same way, g of e2 and g of e3 are 0. So, yeah, you know, I mean, g is just modulo a coordinate transformation. It's just the same thing as f, right? The advantage is that I'm now working that the 3 zeros are now the 3 unit vectors. That gives that means that will help us to understand better how g looks like, how a polynomial looks like when you write it in terms of when you write it as a linear combination of monomials, right? So since A defines a permutation, even a vector space isomorphism, from k to the 3 to k to the 3. These are now little x, little x, little x, little y, little z. So it's a bijection from k to the 3 to k to the 3. Of course, it's even a vector space isomorphism, but that doesn't. It's not important. So by permutation, I just mean bijective map from a set into itself, right? So I just mean that this map is bijective. Okay. So, and because of this, we have that f is PSD if and only if g is PSD. Yeah, it's clear. Since I induce this on Werber and the ring automorphism, right, from this polynomial ring into itself, namely by mapping a polynomial to a polynomial h of a, x, y, z, I'll do exactly what I did here. I plug in for the x variable, I plug in the first component of a times this vector of variables, right? And so on. Therefore, we obtain that f is a sum of squares if and only if g is a sum of squares, right? It's clear because a ring automorphism will map sums of squares to sums of squares, and its inverse also will map sums of squares to sums of squares. So it's easy. It's clear that this is a sum of squares if and only if this is a sum of squares. So in fact, this ring automorphism permutes the quadratic forms. It maps quadratic forms to quadratic forms, and its inverse also, right? Also very easy to see. That's because the entries of A times X, Y, Z are linear forms. And so we see that C is equivalent to G is the sum of 3 squares of quadratic forms. So in fact, now we can reduce entirely to the case, so replacing F by G, we can henceforth suppose that these three vectors, V1, V2, V3, are the canonical basis vectors of a K vector space K to the 3. And now let's, after this prelude, let's now prove the equivalence of these three conditions. Now, C implies clearly B, B implies clearly A, and now we have to go from A to C. So it's easy to see that each polynomial. Okay, maybe let's, by the way, you can perhaps so in this way we can see better, right? So it's easy to see that each polynomial G in one variable T over K, which is non-negative on K, and which satisfies G of 0 equals 0, lies in the ideal T squared, right? Is a multiple of T squared, right? Yeah, I mean, why is this? It's really easy. So you have a non-negative polynomial that vanishes at 0. Yeah, so it has to have at least a double root, right, at 0. But since we are here arguing over an arbitrary ordered field, we have to be careful what arguments we really use. So there are hundreds of ways of doing this, but I said here, let's do it again with 153b. You know, this polynomial has no constant coefficient. And if it had a linear coefficient, so if a linear coefficient would be non-zero, 153b, then the sign around 0 would then be determined by this linear coefficient, right? But that's actually not, but also if you are to the left or to the right, because alpha 1 here would be 1, right? And if you are to the left of 0, we have a different sign when to the right of 0, right? So, and that cannot be because the sign cannot change, right? Because f is non-negative. Okay, so that was really easy thing again. So suppose now that A holds, and now let's really start with a proof. F is positive semi-definite. So I have now this polynomial f, and since vi are the ei's, I know that f vanishes on the axis, right? On the x-axis, on the y-axis, and on the z-axis. It vanishes on all three axes. Now I'm looking, I want to deduce something on the coefficients of this polynomials using also one non-negativity. And therefore I look at, I plug in for one of the variables, I plug in 0, right? That means I look at the polynomials, on the coordinate planes, so on the xy plane, on the xz plane, and on the yz plane, right? And when I dehomogenize it, looking at the polynomial on these planes, so looking at it, at polynomials in two variables, I dehomogenize them. So for one of the two variables, I always plug in 1. And for the other, for Java, I could do nothing, or in fact, I plug in t so that I always get polynomials in t, right? And there are always two ways of dehomogenizing, because I can choose which, with respect to which variable I dehomogenize. So I get first 3 polynomials in 2 variables. And for each of these 3 polynomials, yeah, right, I look at the coordinate planes. And for each of these 3 polynomials, I dehomogenize in 2 different ways. So I get, in fact, 6 polynomials. And I know they are univariate polynomials and they are non-negative. And actually, they vanish actually at 0, right? So I look at all these polynomials. So you see, I plug in so 0 for one of the I plug in 0 for one of the variables, and so there are 3 choices. So I can do it for the last one, for the second one, and for the first one. And for each of these choices, I have 2. I look at 2 polynomials. So, for example, if I plug in 0 for the last coordinate, when I have the xy variables still, and I dehomogenize with respect to x here, and for y I plug in t, or I dehomogenize with respect to y, and for x I plug in t, right? Okay, so I have these 6 polynomials. So if I put the second coordinate to 0, then again I can dehomogenize to one of the 2 remaining variables, and if I plug for the first 0, then it's again the same thing. So I get these 6 univariate polynomials, and I know that actually they vanish all at 0, right? If I plug in t equals 0, then I have always f evaluated at one of the unit vectors, and that's 0 by our hypothesis. Okay, so these are univariate polynomials vanishing at 0 and being non-negative, of course, since f is PSD, they are non-negative. And so, yeah, and so, in fact, the linear coefficients, so the constant coefficients of these polynomials are not there, right? They are 0. And the linear coefficients must also be 0, of course, right? Because, yes, because that was this fact here, right? So they must lie in this idea. Okay. So the coefficients, so what is the, let's see, what's the constant coefficient of this polynomial? So the set variable is not there anymore. And so the constant coefficient of this polynomial, it's the one where y also doesn't appear, when it can only come from a monomial x to the 4, right? So it's actually equal the coefficient of x to the 4 in the original polynomial, right? So I see here that, let's see, so I see that this forces the coefficient of x to the 4 in f to vanish. And what about the linear coefficient here of this polynomial? It comes in fact from x to the 3 y in the original polynomial. So because the linear coefficient of this univariate polynomial is 0, the coefficient of x to the 3 y in the original polynomial is 0, right? And so here, what's the constant coefficient of that polynomial, or where does it come from? It comes from y has been set to 0, so it comes from x to the 4. It comes again from x to the 4, right? So, but we know already that x to the 4 is 0. The constant coefficient of x to the 4 was 0. What about the linear one here? The linear one comes from, so here I have, I said y was set equal to 0, so it's the one coming from x to the 3 set, right? Okay. So here, if I look at this polynomial, so set has been seen, so set to 0, so constant coefficient of this is 0, so that means that y to the 4, the coefficient of y to the 4 is 0. And the linear one of this is 0, so that means that y to the 3x, the coefficient of y to the 3x in the original polynomial is 0. Now comes the next one here. The constant one of this is 0. That means that the coefficient of y to the 4 again is 0, but that we knew already. And the linear one, that means that y to the coefficient of y to the 3 set is 0. Now here the constant coefficient being 0 means that the coefficient of set to the 4 is 0, and then the other one is, since the linear one is 0, we know that coefficient of set to the 3y is 0. And finally, f of t 0, 1, constant coefficient is 0. That means again that that this is 0, coefficient of set to the 4, and otherwise that the linear one is 0 means this. Okay, so I see that because these 6 polynomials are multiples of t squared, I see that the coefficients of these monomials in the original polynomial must vanish, right? So when there are actually not so many monomials, because let's just see what monomials actually. So what monomials are in x and y, just how many are there? So x to the 4, x to the 3y, because of homogeneity, x squared y squared, x y to the 3, and y to the 4, right? And then if we have those where set appears once, when we have x to the 3 set, x squared y set, x y squared set, and y to a 3 set, and those where set squared appears twice, we have x squared z squared xy z squared y squared z squared, and those where x to the 3 appears, we have only z to the 3 appears, we have only these two. And when we have z to the 4, of course, right? But now many of these are already excluded by what we did, right? So this one is excluded, right? This one cannot appear. Y to a 4 cannot appear. Y to a 3 z cannot appear. Y to a 3 z, yes, can also not appear. Y to a 3 x cannot appear. Z to the 4 cannot appear. Z to the 3x cannot appear, and z to the 3 y cannot appear. So there are only, what is remaining is only this one, this one, this one, and this one, and this one. These are only 5, and we're exponents tuple of these 5s, right? So now if I'm determining if I want to say something about the Newton polytope of f, I know the Newton polytope, is the convex hull of all tuples of exponents corresponding to the monomials in f. So here the monomial x squared y squared, this gives rise to this exponent tuple 2, 2, 0. It's x to the 2, y to the 2, z to the 0, right? Then I have here 2, 1, 1. That's this here. 2, 0, 2. Okay, so maybe let's, so this one. Now 2, 0, 2 is, corresponds to that one. 0, 2, 2, to that one. 1, 2, 1, to that one, and 1, 1, 2, to that one, right? So, and yeah, so I have to, so Newton polytope, so I don't know if all these coefficients are actually there. Some of them still might be 0, right? So I know only that the Newton polytope is contained in the convex hull of these, right? Of these. This is now seen as a tuple of real numbers. So Newton polytope is a subset of R to the 3. Okay, and so, yeah, 2, 2, 0. Yeah, actually 2, 1, 1 is superfluous here because it is actually a convex combination of 2, 2, 0 and 2, 0, 2, right? It's just it's just 1/2 times this plus 1/2 times this, so I can actually, it's redundant if I build a convex hull here. And then this 1, 2, 1 is actually a convex combination of these two, right? So you can also forget about this, and this is 1, 1, 2 is a convex combination of these two. So I can forget about these 3 here. So the Newton polytope of f is contained in the convex hull of these 3 points. So 1/2 a Newton polytope of f, which is important to look at in the Gram matrix method, which we will actually employ, is contained in a convex hull of 1, 1, 0. I just divide everything by 1/2. It's just a scaling. 1, 1, 0, 1, 0, 1, and 0, 1, 1. And thus, if I intersect this now with tuples of non-negative integers, then I know it must be contained, in fact, in this 3-element set, in the set of 3 tuples. Why? Because, I mean, if you have something in the convex hull here, then if you have such a vector of length 3 here in this convex hull, then each of its 3 components must be between 0 and 1, of course, right? Because that's true for the generators, then it would also be true for elements in the convex hull. That's easy to see. So actually, there is nothing else possible. Entries can, if your entries should be now integer, then can only be 0, 1 entries, right? So yes. So if we and also sum of the entries must be 2. That's not only true again for these 3 generators, but obviously for every element in this convex hull. So that means there must be 2 1s and 1 0. There is no other possibility, and so actually that's everything that's possible. So now we use the Gram matrix method, right? 2, 6, 1. Now that's of course the important ingredient here. And maybe I should have said right away that we are going to employ a gram matrix method, so it worked over a Euclidean field, and we needed for this to look at 1/2 of a Newton polytope intersected with the tuples of non-negative integers, and it should be if we have a superset of this inside, so if you have a set of tuples of non-negative integers that contains all non-negative integers that are in 1/2 of a Newton polytope, then we can when we can take the column vector of all corresponding monomials corresponding to these tuples alpha I, and that f is a sum of m squares is equivalent to the existence of a PSD matrix, a symmetric PSD matrix over K, such that f equals V transpose GV, right? Where V was this column vector of monomials, and V transpose this is of course the corresponding row vector. Yes, that's the Gram matrix method, and here we have only, here we can take a 3 element set, right? So we deal only with a 3 by 3 matrix then. And that's why we get that it is a sum of 3 squares. But why do we get the PSD matrix? So that will be a very nice argument. So by the Gram matrix method, we have to show that there is a PSD matrix G, symmetric matrix 3 by 3 matrix over K, satisfying this here, right? So I take here now a monomial that corresponds to the exponent 1110 is xy, this corresponds to xz, and this corresponds to yz, and here's the corresponding vector as a row vector, and I have to show that f equals this times this times this for some PSD matrix G. Okay, how to show the existence of this PSD matrix G? Well, first of all, there is, if you forget about the PSD-ness, there is a symmetric matrix G, simply symmetric, satisfying this. Why is this? Well, if you think about it, I mean, if you, by adjusting the entries of G, you can certainly write, so the existence of such a symmetric matrix G is in fact equivalent to the fact that every monomial of f is a product of a monomial in this vector times a monomial in this vector, but it's the same, right? It's the same vector, just once as a row and once as a column vector. So so let's look at the monomials that can appear in F. I mean, those can't appear, we have seen, right? So let's, so what can actually appear? Well, X, if you look just at the monomials in X and Y, this cannot appear, this cannot appear, this cannot appear. So X squared, Y squared, and this also cannot appear. So only x squared, y squared actually can appear. That's the only monomial that can appear, which does not contain z, and that's okay. That's a product of this with itself, right? Okay, so product of this with this, if you want. Okay. So then let's now look at those monomials that contain only x and z. So this cannot appear. And this cannot appear, right? And this cannot appear, and this cannot appear. And so I see again that the only one is x squared, z squared, and that's this times this. And then the last one, if you look, then let's look at monomials that contain only y and z. Y and z. So this cannot appear, this cannot appear, this cannot appear, this cannot appear. So again, it's just y squared z squared. So that's a product of this with itself. It's a product of this with this. So now we still have to check for monomials where all three variables appear. Right? So, yeah, but if all three of them appear, then so what can happen? So none of these monomials is here excluded, right? So, but how many are there? There is just x. So x, y, and z, they all must appear, right? And when I have just one of them must appear with exponent 2 and the other two with exponent 1. So I have just x squared y z, x y squared z, and x y z squared. Okay? These three monomials I still have to check. But yeah, x squared y z, that's this one with this multiplied. So x y squared z, so that's this one with this, and x, that's x y z squared, x y, so here I take x z and y z, right? Okay. So, so we see that there is a symmetric matrix G satisfying this. But why is there a PSD geometric matrix? Well, okay, so actually one also easily sees, if you paid attention, you should have seen it already, that there is a unique such symmetric matrix G satisfying this, right? So that this matrix is unique, first of all, does technically not play a role. We don't need it for our argument. But it gives a little hope. It gives the hope that, okay, if it is unique, then maybe we can show that, we want to show that there is a PSD matrix G. So when we have just to show that this unique matrix G is satisfying this is PSD. And so this gives hope that actually star implies already that G is PSD. Of course, using that F is PSD, right? Yeah, that increases the hope that star, even if G is just symmetric instead of PSD, that star implies that G would automatically be PSD, right? Actually, if G were, that also again I don't need this, but if G were non-unique, when the set of matrices G satisfying this, you see it immediately is an affine subspace of a space of symmetric 3x3 matrices. It's an affine subspace, and an affine subspace, if it contains 2 points, so if G would not be unique, it would be an affine subspace with at least 2 points, but if an affine subspace that contains 2 points contains a whole straight line, right? Namely the one through with 2 points. And if it contains a straight line, then you can easily deduce that it cannot be fully contained in the cone of PSD matrices, right? Actually, in the PSD matrices, it cannot be contained. That's an easy exercise. Again, I don't need this, but if it's nice to show this, and and then. so if it were not unique, I have no hope that it will be automatically PSD, right? So in this sense, it plays a role that G is unique, but I don't really need it as an argument. But from star, it follows now automatically that G is PSD, indeed. So my hope will be, my hope is real, so it's actually real. In order to see this, let V be a vector in K to the 3, and we have to show that that V transpose G V is non-negative. So let me copy this here until the end of the proof. Okay. So we have to show that V transposed GV is non-negative. Okay. Good. So we have to show that V transpose GV is non-negative. Using 751, one reduces to a case where V is actually has no non-zero components. That was this little easy lemma here, right? It suffices to check this for all non-negative, for all vectors without zero components. Without zero components. And if I have such a vector, when I set lambda to be its product of its components, and I set x 1 over v3, y 1 over v2, and set y 1 over v1. It's a little trick. Now I see that v equals lambda times xy, right? Lambda times xz, yz, right? And therefore, V transpose GV is lambda squared xy, xz, yz, xg, xy, xz, yz. And yeah, and then this is lambda square, this is by star is, if I plug in here, we, for x I plug in little x, for y little y, and for z little z. When I get here, this is lambda squared times f of x, y, z, which is non-negative, because f is PSD. And we are done. So let us shortly summarize the idea of this proof. So the idea was basically, you know, we have to show that something which is non-negative is a sum of squares. We use the Gram matrix method for this. And we use information on the monomials. So we actually, after a change of coordinates, we can show that not so many monomials can actually appear in our polynomial. And then the Gram matrix method can be effected with a small tuple of monomials, which is here, and which is, you know, whose effect is actually that the Gram matrix, or a symmetric matrix representing f, actually is automatically positive semi-definite, because when I you know, substitute values for x, y, and z here, I get almost any vector actually, right? Not every, but almost every vector. And yeah, and so a PSD-ness of f implies the implies a PSD-ness of G, and then by the Gram matrix method everything is okay. So that was the idea. So the only problem with this lemma is actually that we have a very strong hypothesis here, right? We have these three projective zeros, if you like, right? If you like to say it like this, for those who like projective space. But yeah. So now let's see if we can cover other cases, because this is a very special hypothesis. So the idea is now, okay, let's try to do similar things under other hypotheses, which are again special, but that are different, so that we can at least cover several cases. So the following proof is very similar actually, but the hypothesis is now different. So let K again be a Euclidean field and F a quartic form. Suppose there are linearly independent free variables, right? The ternary quartic form. Suppose there are linearly independent v1, v2, v3 again, right? And now actually I don't assume that f of v2 is 0, right? So v2 plays a totally different role than before. I still require f of v3 equal to be 0 and f of v1 equal to be 0, right? Because, you know, if you plug in for t0 here, since you require this univariate polynomial, so look at this univariate polynomial, that's a polynomial in t. So I actually look at f, you know, I have f, and I look at v1 and v2. You can think of this as a direction, right? And now you look at this univariate polynomial. That means you look at f on a line, right? So on this straight line, right? Oh, it's not very well drawn. Okay, so right. Okay, and on this line, now this is a univariate polynomial, and I'm saying that this should be in the ideal generated by t to the 3. What does that mean? Well, that means it has a triple root, right? It has a root of multiplicity at least 3, right? So in some sense, f is vanishing to a multiplicity of at least 3 in this direction somehow, right? In this direction. Okay. Okay, so v2 plays the role of a direction here, and so I have only 2 zeros. So I have only 2 zeros instead of 3 zeros. So I have v1 and v3, where f has to vanish, right? And I have now instead of so I have these 2 points where f has to vanish, and it has to vanish with multiplicity at least 3 in this direction, right? Note that if f is positive semi-definite, then this univariate polynomial is also a non-negative polynomial, right? And if it vanishes at v1, like saying f of v1 equals 0, as we did before in the previous lemma, if I said just this, well, that would be actually equivalent to saying that f of v1 plus t v2 is in the ideal generated by t. But since it's a non-negative polynomial, you would have here automatically t squared, right? You would automatically have a double root. If you have a non-negative polynomial, you have automatically a double root, right? So it doesn't matter if you write here t or t squared, right? And in the same way, it actually doesn't matter if you write here t to the 3 or t to the 4. I could also write t to the 4, but formally this is stronger. In fact, it's the same since f is PSD. Right? So yeah, I mean, because of the PSD-ness, if you look at this univariate polynomial, every single root, I mean every root of it is at least a double root automatically. But here I'm requiring more. I'm requiring a triple root, and that's actually then fourfold root, right? At least fourfold, right? Multiplicity at least 4. Okay, so that's the situation here. So again, before in the previous lemma we had this situation, we had 3 roots in projective space, and here we have 2 roots and we have this multiplicity condition. So it's again a very special situation, really very special, okay? And you can do similar things. It gets just a tiny little bit harder, I guess, okay. Almost exactly as in the proof of 752, we can again, you know, since V1, V2, V3 are linearly independent, I should say the fact that they are linearly independent plays, of course, a little role here, because if, so here is the origin, right? So, yes, so I mean, you know, this should be now k to the 3, right? Let's say we have k equal r. And let's look at r to the 3. But I'm drawing only one, you know, I'm drawing only one plane, right? So let's say I'm drawing the plane where the z coordinate is 1, right? That's what I'm drawing. The last coordinate is 1. So that's actually not the origin, but that's the point 0, 0, 1, right? And I'm in this plane here, right? So that's my plane here. And the fact that these 3 are linearly independent means, will be important. So V2, what does that mean? So that means actually that V2 does not lie on this line, right? Or is not a multiple of something that lies on this line, okay? So that means that so that means that V3 is not on this line, and so it's, for example, here. I mean, it mustn't be, it doesn't have to be in this plane, but that's also possible that it is that no multiple of it has to be in this plane. Actually, that's also possible. But if a multiple of it is in this plane, then without loss of generality, V3 is in the plane, and then it shouldn't be on this line. So right. So. Okay. Good. So now let's go to a proof. So it's a special situation. If you don't like all these geometric considerations, there is no problem. Just go through the proof. So from C to B to A, it's of course again trivial. Now from A to C again, one easily sees that the polynomial which is non-negative on K and which is a multiple of, so univariate polynomial in variable t, which is a multiple of some odd power of t, lies in the corresponding, lies in the even power, which is just so where the exponent is just one more, right? So I leave that as an exercise. I already said this. So suppose now that A holds by considering these polynomials, right? It's actually a bit different to what we did before. Before we had last time we had here these 6 polynomials, right? Now we look at a little less. We look at these 4 polynomials, but considering these, we have one sees easily that the coefficients of these monomials in F must vanish, right? So now how many must vanish? It's 6, 7, 8, right? It's 7, 8, but for example, y to the 4 is not among them. So before in the last lemma it was also 8, right? No, it was actually 9. Is it true? Yes, it was actually 9. And y to the 4 was among them. Here it's a bit different, right? I have just 8. But anyway, this will be enough to conclude, we will see. More precisely, the first polynomial is, where is a typo? So, is responsible for the first 4 of these coefficients. So let's look at this polynomial. So here we put the set variable to 0, right? So what remains are the monomials in x and y. When we dehomogenize, when we dehomogenize with respect to x, right? So, and for y we put in t, right? And yes, so if so the coefficient of so now I said as before, VI's are without loss of generality because they are linearly independent. They are without loss of generality. They're unit vectors, right? So if I plug in, so if I have here that f of E1 plus TV plus TE2 is a polynomial that's a multiple of t to the 3, actually t to the 4, but okay. So, and that's actually f of 1, t, 0, right? That's exactly this polynomial. So I know that this is a power of 4. So it's actually, there is only one monomial. So only one monomial which is possibly non-zero. And that one corresponds to a monomial here of f, which is y to the 4. So if you set z equal to 0 in f, then only y to the 4 can be there anymore, right? So that means x to the 4, x to the 3, y, x squared, y squared, and x, y to y cubed. They all must be 0, and that comes all from this, right? And of course from this condition, and also because we can here put t to the 4 automatically. Okay. Yeah, what about this polynomial here? That's E1 plus TE3. Yes. Okay. So the leading coefficient of this polynomial here. Yeah, if you put t equals 0 here, when it's 0, right? Because f of v1 is 0. And so that means that this univariate polynomial lies in the ideal generated by t, and therefore in the ideal generated by t squared, right? And that means that x to x to a 4 again is in the original polynomial, the monomial of x to a 4 is not there, and of x to a 3 set is not there, right? So I get here, from this I would get again this, but I don't care about that because I have it already, and again this, and this. Okay, so the next one is, f if I put here t equals 0, then I get f of e3, which is f of v3. So this lies again in the ideal generated by t squared. And therefore, I know that z to the 4 and y z to the 3 are 0. So z to the 3. Okay. And the last one, f of t01. If I put t equal to 0, then I have f of v3, so this univariate polynomial also lies in t squared, and therefore I get here that this lies so I get again z to the 4, but when I get z to the 3x also. Okay, good. So the third, here it's written again, the third is responsible for z to the 4 and z to the 3y. The last for the coefficients of z to the 4 and z to the 3x. Okay. It follows that the Newton polytope of f is contained in, so let's see. So what monomials are still possible? Let's first start with the ones in x and y. There is only the y to a 4. Right, and then let's look at those that contain z. That contain z. Yes, let's first say z to the power of 1. Then I have here, so x to a 3 set is not possible, and but the others are possible. So x or at least are not excluded. So x squared y z x y squared z and y to a 3 z. This seems possible when those where z appears with a power of 2. These seem to be possible. So x squared z squared xy z squared and y squared z squared. Those where it appears to a power of 3, they are both excluded, and to a power of 4 is also excluded. So so I have these monomials that could possibly appear. So 4, 5, 6, 7. yeah, so let us list all the corresponding exponent tuples. Okay, so this one is corresponds to this one. This one 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 corresponds to this one, and this one corresponds to this one, right? So now certainly the Newton polytope is, so since the exponent tuples appearing in F are exactly this set, right? So the Newton polytope is contained in the convex hull of this, right? But if I'm taking the convex hull, then 1, 1, 2 is superfluous, because it is, for example, the midpoint of a line segment between 2, 0, 2 and 0, 2, 2, right? So 1, 2, 1 is 1, 2, 1 is also superfluous, because it's this 1/2 times this plus 1/2 times this. And 0, 3, 1 is 1/2 times this plus 1/2 times this. So I can forget about these three. So let me cross them here. Cross them out. So okay. Okay, so I have that the Newton polytope is contained in here. That means 1/2 a Newton polytope is contained in a convex hull of 1, 0, 1, 1, 1/2, 1/2, 0, 1, 1, and 0, 2, 0. And thus, if I intersect with non-negative integers, you know, if I take something in the convex hull of these 4 points, right? Then the first coordinate, and if all coordinates are integers, then the first coordinate must be between 0 and 1, because it is like that here also, and the last one also, right? And the second coordinate must be between 0 and 2. Now, let's see. So is it so if the first coordinate is 0, then the remaining ones have to add up to 2, and so it could be 0, 0, 1, but that's not possible actually. If you have something in the convex hull here, in this convex hull, and the first component of it is 0, then it must actually be a linear convex combination of these two, right? But then the second component cannot be 0, so it must be 1 or 2, right? And then if it is you see easily, if it is 1, then it must be this point, and if it is 2, it must be this point. Nothing else is possible, right? So I have these two. With first coordinate 1, we have only these two in this, in this set, in this intersection, right? Okay, and now if the first coordinate is 1, that's the other possibility, right? Then Yes, so when you can take convex combination, yeah, I mean if you are so it must add up to 2. So if you have only, if the first coordinate is 1, since the coordinates must add to 2. So when you have here 1, 0, 1 or 1, 1, 0, nothing else is possible. So 1, 1, 0 is actually not possible because here the second component is strictly smaller than the first, and here also. So you see that you cannot actually reach this with a convex combination that involves, which properly involves, let's say, one of these vectors. But if you don't use one of these vectors, then you are left with these two vectors, but they have 0 in the first component. So you see easily that that's the only possibility. Okay, so now we continue very much in the same way as in the previous lemma. Okay. Okay. So by the gram matrix method again, we have to show that there is a PSD matrix G satisfying satisfying this polynomial identity. So on the left hand side we have a polynomial f, on the right hand side we have this polynomial, which is this line vector of this row vector of monomials times G times a corresponding vector as a column vector. So of course xz corresponds to 1, 0, 1, yz to 0, 1, 1, and y squared to this. So again, it's just a 3 by 3 matrix, which is good, which increases the hope that we can do similar things like before. If a monomial x squared yz actually appeared in F, we would now run into a big problem that we did not have in the proof of 752, because this monomial is not a product of two entries of this vector, right? So it actually, you know, I mean, in the last lemma we had this argument that every monomial that can actually appear, and this actually corresponded to this, or might possibly appear, right? I did not say that they in fact sometimes appear, but they might possibly, at least we did not exclude. So it was exactly for these, if you remember, for these exponent tuples, for the corresponding monomials, we were not sure whether they couldn't appear in F, right? So one of them is x squared yz, right? So if that actually appeared in F, we would run into a big problem. We couldn't proceed as we did in the last lemma, because this monomial is not a product of two entries of this vector, right? And so we wouldn't see why there is actually a symmetric matrix G doing this, because that will be our argument, that we have a symmetric matrix G doing this, fulfilling this polynomial identity. And then we will again conclude that G is automatically positive semi-definite, right? This will be slightly harder only than last time, but yeah, but here we might have a problem. Let's see for the other monomials, actually x squared y, x squared z squared, That's actually okay. That's a product of this with itself, right? Yes. Now the next one, 2, 1, 1, that corresponds exactly to x squared yz. And you see, you cannot write this as a product of something from this with something of this. I mean, it's the same vector, so because you would need, you need x squared, so the only way to do this would be xz times xz, but that's not x squared yz, there is no y appearing. Okay, so here is a problem, so we would have to argue that this actually for some other reason doesn't appear in F. Let's do this later. When here we have xy z squared, that's okay, so you can multiply this with this. When x y squared z, x you take xz times y squared, right? So when x squared y squared, y squared z squared, that's also okay. You take yz times yz, and when y to a 3 z, that's also okay. So you take this times this, and when y to a 4, you take this times this. Okay, so the only one that poses a problem is this one. But this coefficient of x squared yz actually is 0. Okay, so why is this? Okay, so for this, write f as, you can write, every monomial of f has degree at most 2 in x, right? So the power of x, the exponent of x in every monomial of f is at most 2. You see it here, right? It's a convex combination of 2, 2, 1, 1, 0, 0, 0, right? So I have here, so f can be written as g times x squared times h times x, plus, let's say I times, plus I, where g, h, and I are polynomials in y and z, okay? And g actually, because g can be chosen, of course, to be homogeneous of, so g, h, and I are, so g can be chosen as a 2 form, of course, right? H as a 1 form, a linear form, right? And I as a 0 form, so constant. Okay. And because f is homogeneous of degree 4. And so you see that, so actually we know already that some monomials where x squared appears are actually not, do actually not appear in f, right? So some monomials which are multiples of x squared do not appear in f actually. So so we only want, theoretically there are 3 possible monomials, so there is something like, there is y squared, so g is of the form a y squared plus b yz plus c z squared, right? With a, b, and c in k. I can write g in this way. But you know, here you see that these were the tuples of exponents of monomials that possibly appear in F. And the only one where I have where x appears to the power of 2, the only monomials are z squared and x and y z. So sorry, x squared. So x squared times z squared and x squared times y z. So there is one here that actually is already excluded, right? That one is already excluded. Good. So now, and what do we have to show? We have to show that this monomial does not appear in F. So we have to show that b equals 0, right? To show that b equals 0, right? And for this I use that g is actually non-negative on k squared. Why is this? Well, if you plug in for g some value on k squared, so some pair of numbers from k, then in case that so let's do this. So for y and z in k, we have actually either g of yz is 0, right? Or it is non-zero, but if it is non-zero, or it is non-zero, and it is the leading coefficient of f of x, y, z, right? Clear, right? Of this univariate polynomial, which is a polynomial in X. But this univariate polynomial here is non-negative, of course, right? So therefore, it's non-negative on the whole of K. So therefore, its leading coefficient has to be positive, actually, right? So I get that g of yz is 0 or positive, okay? Okay. Yes, and and actually maybe it's technically a little bit easier if I plug in here, if I take z equal to 1, right? So maybe we don't even consider z. I mean, g is homogeneous, so it's not surprising that I get almost all information by setting z equal to 1, right? And so so if I plug in here g of capital Y, 1, when I see when this goes away and this goes away, right? And when I see it's just a linear polynomial, a linear univariate polynomial, which is non-negative, right? Since I said this is non-negative. And yes, and when this is non-negative on the whole of k can of course only happen if b equals 0, if it's actually a constant polynomial, right? Okay, so that's the argument. So here in the lecture notes I just wrote this coefficient vanishes, as one easily shows, since for all y and k the leading coefficient of this is non-negative, since this polynomial is non-negative on k. Okay, so as in the proof of 752, one sees again that there exists a symmetric 3×3 matrix over Kg satisfying star, just symmetric at the moment, right? And when the hope is that it is automatically positive semi-definite. Yeah, one could again argue, or one could see easily that G is unique, but we don't need this for our arguments, right? Just as in the last lemma, however, I explained, right, that if it were non-unique, then the type of argument we are going to make could hardly go through. So in that sense, it plays a little role. Or I just wrote it so that we can understand better what's going on, but I don't really need it. And if you want to see why G is unique, well, that's all monomials that can appear in F. For every monomial that can appear in F, there is a unique way of writing it as a product of one of these three monomials. Just check it again. And from star, it follows automatically that G is positive semi-definite since F is PSD. Right? One might think that this is not so clear because for example, the third component of this vector here, if I plug in values in K for X, Y, and Z, is always non-negative, right? Yeah, so it seems a bit, doesn't seem so clear. However, that turns out to be not much of a problem. And in fact, the argument is very similar to last time. So to show that V transpose GV is non-negative for all vectors V in K to the 3, we could reduce to the case where all components are non-zero, just like we did last time by using this trivial lemma 751. In fact, here it's enough to reduce to the case where the second and the third component are non-zero. We just don't need. For the first component, we don't care actually. And this time we set lambda to be V2 squared V3, and now since V2 and V3 are non-zero, we can divide by them, and I set X to be Y1 over V2 squared, Y is 1 over V2, and Z is 1 over V3. And now V is, yeah, by the way, I said, maybe I should say this also. I said that it's a bit surprising that it works because the third component, if I plug in values here, is always non-negative in K. But I mean, you can write here a minus and here again a minus, right? So after all, and then, and then you get, in this way, you get here also vectors which have a negative third component. So in fact, we just have to check that it works out, right? Okay, so I said little x, little y, and little z like this, and when v equals lambda x z lambda y z y squared, because why? Lambda times xz is, xz is, yes, that's v1, right? Lambda times yz is v2, and lambda times y squared is v3 by construction, right? And therefore, v transpose gv equals lambda squared times this vector g times this vector, and by star this is lambda squared f of little x, little y, little z, and since f is PSD, this is non-negative, and the square is also non-negative, so I have something non-negative. And I've shown that v transpose gv is non-negative, and that was for almost all these vectors, and that's enough to show that G is PSD, right? So automatically it is PSD. Okay, so now we are not yet done. We continue this type of arguments. So in the next lemma, Okay, so so in the next lemma, it's again almost the same situation. So we have here, but so you know before we had here that f of v3 equals 0 and v3 was not in the span of v1 and v2, right? Now we have here something in the span of v1, v2. In fact, we have v2 simply, right? And otherwise, it's exactly the same thing. When again we have the same statement, okay? So that's another case of the same story. So again, without loss of generality, v1 and v2 are the first two unit vectors this time. I have only two vectors now. C to B to A is again trivial, and now A to C goes again with the gram matrix method. One uses again that a polynomial, univariate polynomial G in T, which is non-negative in K, and is a multiple of an odd power of T, lies in the, you know, in the even power that follows the odd power somehow, right? Or lies in T to the even power that follows this odd power. Suppose now that A holds, by considering the following polynomials, one can see easily that V's coefficients in F must vanish. Why? So here I set z equal to 0, so I'm investigating the monomials which have just x and y, which are just monomials in x and y. But you know, that's actually f of v1 plus tv2. It's exactly this polynomial now, right? Since v1 and v2 are the canonical basis vectors of a k-vector space k to the 3. So that's now a multiple of t to the 3. And what and then therefore a multiple of t to the 4, right? Because it's a non-negative univariate polynomial. And so you see that yes, you see that if you look at monomials in x and y only, when the only one that can appear possibly at seems to be y to the 4. We will later exclude it, but for the moment we exclude the other ones. This one, this one, this one, and this one. So for the next here, now I'm setting y equal to 0, so I look at monomials in x and z. And yes, since yeah, I mean, if I set t equals 0, when I have f of a first unit vector, and that's clearly 0 if I plug in 0 here. So f of v1 is 0, of course. And now that means that the constant term of this polynomial is 0. And also a linear term because of PSD-ness, right? Yeah, and the linear term also has to be 0, since it would otherwise determine the behavior of the sign in near 0. So we have here that constant and linear term are 0. So we have that x to the 3 set, and that comes from a linear, and x to the 4 again, right? That comes from a constant one. I see that these two are 0. I mean, for x to the 4, I've had already seen it with the other polynomial. So the next one, f of t1, 0. So I plug z equal to 0. So I'm investigating monomials in x and y. And yeah, again, if I plug in t equal 0, when because of f of v2 equals 0, this is 0, right? So and since this is a non-negative univariate polynomial, it has no constant and linear term, but it has no constant term amounts again to the fact that the coefficient of x to the 4 is 0, and for the linear term it amounts that the constant term is non-zero amounts to the fact that f of y is that the coefficient of y to the 4 is 0, and the linear one that's x y to the 3 again, but that one I had already. And now this thing here, f of 0, 1, t, if I plug in 0 here, I get again f of v2. So, and this time, this polynomial, yeah, this shows that, this shows only something about the monomials in y and z. And actually it shows that y to the 4 and y to the 3 set are 0. That comes from a linear term of this polynomial, and that comes from a constant term here. So, okay. Yeah, here it's written again. The first polynomial is responsible. Sorry, this is actually a typo again. Is responsible for the first 4 of these coefficients. The second one for the coefficient of x to the 4 and x to the 3 set, and the third for the coefficients of y to the 4 and x y to the 3, and the last for the coefficient of y to the 4 and y to the 3 set. It follows that Newton polytope of f is contained. So what monomials can actually appear in f still? Well, let's see. So the only one that in x and y, which so no monomial which contains only x and y as variables, right? Because they are all forbidden already, and so z has to appear everywhere. So if z appears to the power of 1, so if z appears with exponent exactly 1, then again 2 are excluded here, namely x to the 3, y to the 3 set, x to the 3 set, y to the 3 set. So what is still possible is x squared y z and x y squared z. And I think that's it, right? So these are the only tuples of exponents belonging to monomials, to potential monomials in f, where z appears to the power of 1. Now if z appears to the power of 2, so if I have z squared in the monomial, then I have here x squared z squared. So let's see, so if here x squared z squared, here y squared z squared, and x y z squared is this one, right? Okay, and then if z appears to the power of 3, then I have if z appears to the power of 3, there is only these two, right? Y z squared and x z, y z to the 3 and x z to the 3. And then if z appears to a power of 4, there is only this one, right? So these two, and then last one is this one. Okay, so these tuples of exponents are all that belong to possible monomials of f. That monomials that could appear, at least theoretically. Now, when if I take when the Newton polytope of f is contained in the convex hull of V's, but for the convex hull I can forget about this, because this is this is if you add these two, if you take 1/2 times this plus 1/2 times this. No, sorry. If you add this to this, right? If you add these two and you take 1/2 of it, then you get that one. So you can forget about that one. That's redundant to build the convex hull. This one, 1, 0, 3. So for this, if you take 2, 0, 2 and 0, 0, 4, if you take 1/2 times this plus 1/2 times this, it's this. So you can forget this also. And then 1, 1, 2. So you can take 1/2 times this plus 1/2 times this is this. So it's also a convex combination of others in this list. So you can forget about these three. And now 1/2 times the Newton polytope of f is contained in the convex hull of 1, 0, 1, 1, 1/2, 1/2, 1/2, 1, 1/2, 0, 1, 1, 0, 0, 2. Okay. So now if I look just at integer tuples in there, that's what I do in the Graham matrix method, then I can, the first, if you have anything in this convex hull here, the first and the second component of it must clearly be between 0 and 1, right? And the second component actually between 1 and 2, okay? And the sum must be 2, of course, always, right? So if the first component is 1, then it could be 1, 0, 1 or 1, 1, 0. 1, 1, 0. But 1, 1, 0, you see it's actually not possible, because if in a linear combination one of these actually appears with a non-zero coefficient, when if you have a convex combination of these 5, where one of these 4 appears with a non-zero coefficient, when you never get the 0 at the end. You cannot get 1, 1, 0 in this way. You can only get 1, 0, 1 in this way. Okay, so if the first component is 1, the two others have to be this. So now I know that the first component otherwise can only be 0, right? If it's 0, then let's look what the second component does. If the second is 1, then the third has to be this. If the second is 0, then the third has to be this, because the sum is always 2. Okay, so I see that the integer tuples in 1/2 and Newton polytope of f are at most these 3. So by the Graham matrix method, again, we have to show that there is a positive semi-definite matrix G, symmetric matrix over of size 3 over K, such that star holds, right? If you want to show that that f is the sum of 3 squares. Okay. So again, we first want to show that we have here that we can do it with a symmetric G, and then that this symmetric G is automatically positive semi-definite. So these are all the possible monomials in F. I mean, these are their tuples of exponents, as we had seen. So at most these, right? So for example, now that such a symmetric G, if such a symmetric G exists, means just that, if you think about it, that I can write all these monomials that correspond to these tuples as a product of these three monomials, right? As a monomial from here times a monomial from here. Well, that's the same vector anyway, right? So let's look at this. So that's x squared z squared. We can write this as this times this, right? In fact, it's not important for our argument, but there is always a unique way of writing these monomials here as such a product. And in fact, you see that it's just x squared, z squared, right? It's just a product of this with this, no other possibility. As I said, the uniqueness is not important, but let us note it for some reason. Okay, so now x squared y z. Oh, I cannot produce this, right? That seems to be a problem. So x squared y z seems to be a problem, right? So the next one is x y squared z. X y squared z actually can't produce this, right? So seems to be a problem again. So we have to show maybe that these two, we have to show that these two don't actually appear in F for some other reason, right? Okay, so now this one, that's y squared z squared. Y squared, that can actually be done by multiplying this with this, and there is no other way of doing it, right? And then y set to the 3, well, that's this with this, and there is no other way of doing it. Well, there is always the symmetric way, of course, right? But z squared y, I mean, that's clear. But so y is z squared, right? And then z to the 4, well, that can only be done like this, but it can be done, z squared times z squared, and x z to the 3, well, that can only be done by xz and z squared, and then xy z squared. That also can be done in a unique way by multiplying xz with yz, or vice versa, right? So the problem seemed to be these two monomials. So if these appeared in F, you would have trouble, since these monomials are not the product of two entries of these. But these coefficients vanish, as one easily shows. It's in fact an argument which is again very similar to what we had in the last lemma. Right, since so if you remember in the last lemma, we had here we had shown that the coefficient of x squared y z is actually not 0. So that's actually the same. It's actually the same monomial as here, right? And but we have to be careful, because last time the argument was really that that we also used. It also depended on what possible monomials could there be by this argument here in the beginning. So let's just do it again. And actually we have to do twice the argument, right? Okay, so here we do it for this, and here we do it for this. And this time the argument is that I can write f as, I write it again as a polynomial in x with coefficients which are polynomial in y and z, right? So, you know, and here something constant, right? So these should be in the polynomial ring over y and z. Sorry, something constant, that was not the right way of saying it. It's polynomial in y and z, right? Yes, and if you look at, so theoretically we would have here something like a times, y squared plus b times y z plus c times z squared, right? But there is already, you know, x squared y squared, x squared y squared would correspond here to a tuple 2, 2, 0. That's not here, right? So that actually, this term, this first term, can actually not appear here. When the others, when the other one, so x squared y z, that would be 2, 1, 1. If I see it as a tuple, that's actually here. And x squared z squared, that's 2, 0, 2. That's also here. So maybe these two could appear a priori, right? And, you know, since... yes, and I have to show that b is 0, right? To show b 0. B is 0. And but you know, I know that that if I plug in for set 1, right? So when we're okay, so if I look at f of x comma y comma 1, when this is a univariate polynomial in x, and I can write this as by plus c times x squared, and then plus lower order terms, right? Lower degree terms in x. And if this is not 0, then it is the leading coefficient. And if it's the leading coefficient, since this univariate polynomial is non-negative, since f is BSD, is positive. So in all, this is always non-negative, right? But that's only possible if b is 0, of course, right? Okay, so that's the argument here. And for the other thing, I have here f. So in order to prove that this is 0, I write f as, also the exponent of y is at most 2, right? So I can write f here. I expand it as a polynomial in y if you want, right? And I have here, theoretically I had here a x squared plus b xz plus c z squared, right? And here is something in x and z, sorry. So these should all be polynomials in x and z. But I know already, let's see what monomials are actually are not excluded already. So x squared times y squared, that would correspond here to 2 to 0. Yeah, that that's again excluded, right? That's again excluded. So, and if you want, I don't care about if the others are excluded already, but now I can do the same argument, right? But because what do I have to show? I have to show I want to exclude the monomial xz times y squared, so I have to show that b equals 0 again, right? So again, I have to show that b equals 0. And again, f of this time I look at f of little x, capital Y1, so I plug in a little x from k for x and 1 for z, when I get that this is bx plus c times y squared plus terms of lower degree in y, so it's a univariate polynomial. Now, if either for each fixed little x, this is either 0 or it's the leading coefficient of a quadratic non-negative polynomial. So all in all, it's non-negative. And for all x, actually, for all little x from k, and that can only happen, of course, if b is 0, and we are again done. Yeah, so I see now so I see now, since this problem is resolved with these two monomials, I see that there exists a symmetric matrix G satisfying star here. And in fact, again, G is unique because there, for every potential monomial in F, there is a unique way of writing it as such a product, you know. But that doesn't play a role, as always, but yeah, I had argued that if this weren't the case, then I would probably run into problems with the argument I want to make here. So from start it follows automatically that G is PSD, since F is PSD. To see this, let V be again an arbitrary vector in K2 or 3. Now, the argument is very similar again. So one can reduce to a case where the last two components of this vector are non-zero. I set lambda equal v2 squared v3. I can now divide by v2 and v3. So x is, I can set x to be v1 over v2, v3. Y 1 over v3, set 1 over v2. So then, of course, x times z is lambda times x times z is actually, by the choice of lambda, is exactly v1, right? Lambda times yz is clearly v2, and lambda times z squared is v3. So v is lambda times this, and therefore now we have the same argument as always. V transpose GV is lambda squared times this, G times this, and by star this is lambda squared f of x, y, z, which is non-negative since f is PSD. And we are done, right? We have shown that G is positive semi-definite. Okay, so we have now the three lemmata. These three lemmata, which are all very similar, and we will actually use all three of them for the next lemma, which is very important step of our proof. Okay, so the next lemma is the following. So let F be a ternary quartic, a positive semi-definite ternary quartic form. that is not a sum of three squares of quadratic forms, right? And that has two linear independent zeros. When there is a linear form, so you could say in projective space, for those who like projective space, it has two zeros. When there is a linear form L, which is not a zero form, such that f minus L to the 4 is positive semi-definite. Okay, so yeah, that will be a very important step in our proof. So so we use now already the first of these three lemmata. So by lemma 752, the zeros of f span a two-dimensional subspace of R to the 3. I mean, there are two linear independent zeros, right? So I know that the zeros of f, and here I mean, of course, the zeros in R to the 3, span either the space generated by these two linear independent zeros, or always span the whole of R to the 3. But by lemma 752, the first of these possibilities actually takes place, right? So 752. Okay, so here the lemma now is over the real numbers, but the real numbers form a Euclidean field. And so suppose that here if there were, so all we have to show is that there are not three linearly independent zeros, right, in R to the 3. But if there were, when with this lemma, I could, the PSD-ness of f would be equivalent to f being a sum of three squares of quadratic forms. And since f is supposed to be not such a sum of three squares, but f is supposed to be PSD, we know that there cannot be a third zero, which is not in the span of the other two. Okay, I mean the span of two which I fix. There might be some others in this span. Okay, so and when everything here, what I'm claiming here is of course again invariant under a change of coordinates. Right, so I can actually, because if I have, for example, an invertible matrix A in GL3 of R, it's an invertible 3 by 3 matrix over R, when, I have this, on one hand I have here this vector space homomorphism. This is a vector space homomorphism. Isomorphism, actually, sorry. On the other hand, I have here this orthomorphism of a polynomial ring. That maps a polynomial to P of A x, y, z. So that's a row vector with variables x, y, z, and I can multiply this with this real matrix. And when I get again it's a column vector. And when I get again a column vector, and I can substitute, and what this means is that x is replaced by the first entry of this column vector, y by the second, and z by the third, and so on. And this is a ring automorphism. Ring automorphism. Mapping. Mapping four forms to four forms, quadratic forms to quadratic forms, linear forms to linear forms, in general mapping k forms to k forms for each k. And so if you want to write down the details why I can reduce to the case where the two linear independent zeros here are the second and the third canonical basis vector, then please you can do it with the ingredients I just gave you at hand. And now so I know that so outside the, maybe let's now draw a picture. So I have here the x-axis, and when the y-axis, I consider it to be orthogonal to the plane where I'm drawing now, right? So here is the origin. So the y-axis should be orthogonal to the plane where I am drawing, and then here I have a z-axis which is actually in the plane where I'm drawing. Okay, and now I have that yes, on the second and third canonical basis vector I have a 0, right? Because of homogeneity of this four form, I know that on the y and the z-axis, f vanishes, right? So let's say here f vanishes on these two axes. Okay, and f is doesn't vanish anywhere else outside the yz plane, right? It might perhaps vanish somewhere else in the yz plane, but it doesn't vanish outside the yz plane, right? So f is positive. I could write here maybe outside. Just outside the yz plane. That means for all points where the x-coordinate is not 0, right? Okay, we now claim that there is some epsilon bigger than 0 such that f minus epsilon x to the 4 is positive semi-definite. And when we are done, because when we can take the fourth root of this positive epsilon, right, and the fourth root of it times x is then our linear form that we are looking for. Yeah, this linear form vanishes, x vanishes exactly on the yz plane. So, and yeah, on these two axes, the y and the z axis, our linear form has to vanish now, because otherwise we don't have a chance to squeeze it in here, because epsilon x to the 4 must, or epsilon or L to the 4 must be less than or equal f, and in fact is PSD itself. So therefore, if where f has a 0, L also has to have a 0, of course, right? So it vanishes on, and if a linear form actually vanishes, it has to vanish. The linear form we are looking for now has to vanish on the y and on the z axis. And if a linear form vanishes on the y and the z axis, because it's just linear, when it vanishes on the whole YZ plane, right? So actually the only linear form we could have tried with now is x, or is a multiple of x, right? And that's what we do. Okay, so now we have to check that f minus epsilon times x to the 4 is PSD for some positive epsilon, right? Okay, so now by homogeneity, right, because everything is homogeneous, it would be actually enough to check with non-negativity instead of on all of R2 just on, for example, the unit sphere or something like this, right? And here I actually take the unit cube. So more exactly, I take this set, so that's like, filled unit cube if you want, closed filled one, and when I take away its interior here, and then so I get a boundary of it, so I get the union of the sides of a cube, right? So that's better suited when a sphere, so and it is compact also. Okay, so yes, so now let's continue over there. So let me copy this. So the idea is, of course, that the compactness enables us to reduce to showing that this epsilon we are looking for, such that f minus epsilon x to the 4 is non-negative, that we need to find this only locally, right? So we will see later how we go using the compactness from local to global. So anyway, we have 6 sides of this cube, right? I mean, actually, since f is a form of even degree, and so it would actually be, and L to the 4 also, so we would actually be able to work with 3 sides here, right? 3 sides, none of which is opposite to the other, right? But anyway, let's do it with 6 sides, doesn't matter. Okay, so for this purpose, so for showing the existence of this epsilon, it is enough to show that for each 2-dimensional face of this polytope, that means for each side of this cube, there is, polytope is a convex set generated by finitely many points. Polytope in R2/3. Here it's generated by it's a convex hull of 8 points, right? So it's a polytope. It asks for each side of this cube, where is this epsilon, right? So we have to show it for each side. That's the first step. And then on some sides, that will be easy. On other sides, we will have to argue locally. On the 2 sides, on this one, which is parallel to a YZ plane, and on the opposite one, which is also parallel to the same plane. So on these 2 sides, it's easy, because f is positive on these 2 sides, right? On this side and on the opposite side. So that the existence of such an epsilon follows from 7.1.19, because a continuous, because both these sides are compact sets, they are bounded and closed, right? And so from a continuous function on a non-empty compact set assumes a minimum and a maximum. In this case, I'm interested in the minimum. no, actually also in the maximum, because L to the 4, well, L to the 4 is, L is x, right? So L to the 4, yeah, I don't need 7, 1, 19 to see that. So x, L to the 4, which is x to the 4, actually is constantly 1. If it weren't constantly 1, then I could argue with this maximum that it takes on a maximum, but I don't need this. But anyway, f takes on a minimum, right? By 7, 1, 19. And when this minimum is positive, and then I can define epsilon to be this minimum. So for these two sides, for this side and the opposite one, it's trivial. After a further change of coordinates, it suffices to consider from the remaining four sides just this one, right? For which the z coordinate is 1. So it's actually, it's one which I color here in yellow. So this yellow side here, why does it suffices it to treat that one? Okay, I could, if I have one of the other three, I can bring it to the top of this cube, right? By rotating the cube along the x-axis, right? Rotating the cube along the x-axis. That's a linear change of coordinates, an orthogonal change of coordinates even. That leaves the pair of axes y, z, which maps this pair of axes to itself. So these two zeros of, the fact that f vanishes on these two axes, it's preserved. Yes, so without loss of generality, I'm just looking on that side of a cube now. That's the yellow one, the top one. And consider therefore f tilde. F tilde is now where is the dehomogenization of f with respect to the third variable, right? So I set the third variable, the z variable, to 1. So I'm actually in the affine space, which is spanned by this yellow side of a cube in the z equal 1 plane, right? Okay, so from lemma 754, we deduce that if I take now, so now comes the second lemma, right? The second of these three lemmata we use, of these three similar lemmata. Okay, so I take the second derivative of f tilde in a point 0 y, where y is a point where f tilde of 0 y equals to 0. And I deduce from the lemma that the second derivative in this 0 of f tilde, that the second derivative of f tilde with respect to y is positive. Okay, so what does that mean? What the point 0 y? Well, in the plane they are, of course, on the y-axis, right? That would be a point on the y-axis if you consider the xy plane. Now, thinking how f tilde was defined by setting the z coordinate to 1, we could, of course, also think of a function f, of a function that f defines, that we look at that function in a point which is on the parallel of a y-axis here, right? So maybe I should actually draw this parallel of a y-axis that goes, instead of through the origin, goes through the point 0, 0, 1, right? Maybe let me draw the point 0, 0, 1 here in orange. So that's the point 0, 0, 1. 0, 0, 1. And let me draw a parallel to a y-axis through this point. It's not very well drawn. So, okay. And that's a parallel to the y-axis. And so what I'm looking at is points on this parallel, if you want, right? And I'm looking at zeros of f on this parallel. That means I'm looking at zeros of f tilde on the y-axis, right? And when I take, because f is non-negative everywhere, if I have a 0, then the first directional derivatives in this 0 have to vanish, of course, right? And now, but here I'm looking at the second directional derivative in direction of y, in direction of 0, 1, right? If I'm speaking about f tilde, but if I'm speaking about f, then it would be the direction 0, 1, 0, right? The direction of the y-axis. So I'm looking at, zeros here. Yeah, so the thing is the following. So I want to find this epsilon that works on this yellow face of a cube. And on this yellow face of a cube, f is everywhere positive. So locally I will be able to find this epsilon easily outside of this orange straight line here, right? That's why I'm looking at zeros on this orange straight line. And if I have a 0 here, when I know that the first directional derivative, the directional derivative in this direction vanishes, the first derivative, but the second directional derivative into the same direction actually will be positive. That's what I say here. And this follows from lemma 754. Why does that follow from lemma 754? That's the second of our series of 3 lemmata. So I will apply this to f, right? So because I know that f is PSD, but f is not the sum of 3 squares of quadratic forms. By hypothesis, I know that there are no 2 linearly independent vectors v1, v2 satisfying this, right? So, and what are these vectors? I will use it. So actually I will apply it with v1 equal to this point on the orange straight line here, on this parallel to the y-axis, right? And with v2 will be just indicating the direction, so 0, 1, 0, right? Right, because then what does that mean? That means actually, if you think about it, that means exactly that the second derivative of f in the point v1 directional derivative in the second directional derivative in direction of v2 at the point v1 of f vanishes. I mean, okay, it means that f, its first directional derivative and the second directional derivative vanish at the point v1 in direction of v2. Okay, so yes, so yeah, so and this cannot, so because the conclusion of lemma 754 is not true here, this must be violated or this must be violated. Well, that's not violated, right? Because f vanishes on the y-axis, right? Okay, so we have that lemma 754 implies in fact exactly this for all y in R that satisfy f tilde, okay, f tilde of 0y equals 0. You know, if f tilde of 0y equals 0, if first, that means I have a 0 there. Because of a non-negativity, I have when that the first derivative in direction of a second unit vector also vanishes. And then the second cannot vanish anymore, okay? So I apply 754 to f. v1 is 0y1. v2 is 0, 1, 0, 1, 0. And I take into account that if this, if the function itself vanishes at 0y and the directional derivative here vanishes when the directional derivative vanishes, because f tilde is non-negative on R2. In the same way, now so I know now that second directional derivative here along this axis is positive in every 0, right? So but if I now take another direction, if I take a direction like this, or like this, which is so meaning that if I have a y in R satisfying again f tilde of 0y equals 0, all other directional derivatives of f tilde in 0y are also positive, right? I mean, in the original picture, in the three-dimensional space, this means that directional derivatives of f in directions that are parallel to the xy plane are positive at every 0 of f on this orange straight line. So how do we prove this? So such a direction here is given, a direction which is not parallel here to this orange straight line is given by, and that's a direction actually which is in this z equal 1 plane here, right? So it's a direction, let me call it v2, of a form x it has some x component, right? So something, let me say, different from 0, and then something, right? Anything, and then 0, okay? And then now I want to use actually lemma 753, which was, probably the first one. I get confused about which lemma is which. It was the first of a series of 3 similar lemmata. Let's see. No, sorry. Yes, it was the first one. Yes, exactly. Okay, so, and in this lemma 753, I needed a V1, a V2, and a V3, linearly independent. And V2 was this direction, right? Because here I go, I start at V1, I go in direction of V2. If I look at that univariate polynomial, right, it's so this should be a multiple of t to the 3. That means it should have root, at least a threefold root. That means the polynomial itself, the first directional derivative into this direction and the second directional derivative have to vanish. That's what it means. Yeah, and so that's one thing. So I need this point where this and this direction where the corresponding directional derivative in this point vanishes. The function itself, the first derivative and the second derivative all vanish. Now, and then I need another point where f simply vanishes, right? So, okay, so what points do I take? So this will be the direction. V1, of course, will be 0, y1 for some y, indicating this point here. And then V3 will, of course, be should be something so that these 3 things get linearly independent. I can take I could take 1 0 0 1. So there are 2 candidates, 0 0 1 or 0 1 0, right? Because I know that on the y-axis and on the z-axis f is 0. And so which one should we take? So we should take the one that makes sure that these 3 vectors, v1, v2, v3, are linearly independent. And I guess that's good with both choices, right? So for v3, take either this one or this one, and then v1, v2, v3 will be linearly independent, as you can easily see. Okay, so altogether, f tilde was only zeros in the plane at which the second derivative is positive definite. That means the Hessian is positive definite, right? Because the Hessian, of f, let me denote it by, or of f tilde, sorry, so let me denote it by h f tilde, the Hessian at some point, right? At some point, x, let me call it x, or let me call it v, and is a symmetric matrix, and if I multiply it from the left with a row vector v transpose, and from the right with the same vector as a column vector w transpose and w, when this is, that's the directional derivative in direction w of f tilde at v, right? And since all directional derivatives here are positive. This is positive for all non-zero w, right? In this point. So the Hessian is positive semi-definite. Recall, by the way, that all zeros of f tilde lie on the y-axis, right? Because, so on the affine space spanned by this yellow side of a cube here, that means in the z=1 plane, the only zeros of f lie in this orange straight line, right, which is just which arises from the y-axis by moving it up until it hits this, until it is contained in this z=1 plane. Okay, so this Hessian is positive definite, and then from your calculus, multivariate calculus course you have taken probably in the second semester or even first one, I don't know. We know well, we know only once, not twice, that each zero of a non-negative polynomial f tilde in R squared, or equivalently in 0 cross R, right, which is, which would be the y-axis, is an isolated global minimizer. An isolated global minimizer. That means that since a global minimizer, it minimizes f tilde on the whole of R squared. Because f tilde is non-negative on R squared, but if I have a zero, it's of course a global minimizer, right? But it's an isolated one. That's the important thing here. Isolated means that in a neighborhood of this minimizer, there is a neighborhood such that on this neighborhood we have just a unique global minimizer. Okay, so we have a whole neighborhood where f is positive except in the point, right, except in this zero. Okay, so therefore, if you look at the set of zeros of f tilde, that's, they all lie on the y-axis, so you can write them like this. So there is a positive integer m and y1 up to ym in R, such that this is the case. And one of the yi's is of course 0, by the way, because my function f was vanishing on this z-axis, so the f tilde vanishes at the origin, right? Okay, since minus x to the 4, right, as well as its first and second derivative vanishes on the y-axis, right? So yes. With second derivative I mean the Hessian now, right? With the first one I mean the gradient. You could also say all first partial derivatives and all second partial derivatives. That's the same thing. Yeah, let's look at it. So it vanishes on the y-axis. That means it vanishes. So the first partial derivative of x to the 4 is 4x to the 3, the second one is 0. And on the y-axis this vanishes, right? This of course also. When the second partial derivatives, okay, if I take here again a derivative with respect to x, then I get 12x squared. If I take the one with respect to y, I get then 0. And if I take the second derivative with respect to y, I get also 0. So, you know, the Hessian of x to the 4 looks like, at the point xy, looks like with 4x to the 3, 0, 0, 0 at the point xy, right? Doesn't depend on y, actually. So, and this for x equals 0, that's 0, right? And for the gradient, the same thing, right? Because for x, if you plug in here for x 0, and it vanishes, this vanishes. Okay, so, yeah, so every 0 yi is a 0 and an isolated local minimizer of f tilde minus x to the 4. Okay. So, yeah, by the way, why did I have here isolated global minimizers? Well, I had global minimizers. I think I didn't even say this. Why are they isolated? Well, because the Hessian was positive definite, right? And yeah, so that's just calculus course, right? It's an isolated global, it's an isolated local minimizer. So that's if you have that the gradient vanishes, the gradient actually must vanish, right? And you have that the Hessian is positive definite in the same point when you have an isolated local minimizer here by multivariate calculus. And since it's a global minimizer, it's an isolated global minimizer, of course. Okay, so here I can employ the same thing, the same fact from multivariate calculus, and I have an isolated local minimizer of f tilde minus x to the 4, right? Here I know only that it's local, right? Cannot say it's global, okay? Now choose for each I in 1 to m an open neighborhood ui of 0 yi, such that f tilde minus x to the 4 is positive on ui except at the point 0 yi. Yeah? That can be done because of this isolated local minimum, right? So what I have here now is, I have here on this orange straight line, I have certain zeros, right? One is actually here, right? I have finitely many. And yeah, and when I have these ui's in this picture, they would be, you know, they are actually subsets of R2. But in this picture, of course, it's convenient to move them into a set equal 1 plane. So let me do this, right? So I have here these ui's, these neighborhoods. I can choose them open, of course. That will be convenient for later, such that f tilde minus x to the 4 is positive on the whole on these neighborhoods, except at the zeros themselves. Right. In fact, maybe I'm only interested in the zeros which are here on the yellow side of the cube. In fact, but anyway. When of course f tilde minus epsilon x to the 4 is positive for all epsilon less than or equal 1, right? That makes it can make it only better, right? On the same set, ui without 0 yi for all I. And choosing epsilon smaller is better for if I want to look again at the whole yellow side of a cube. Since f tilde is positive, namely on the compact set, you know, on this square, without the union of the ui's, right? So if you want, you could yes. Yeah, here yeah, I mean, it would be okay also for the, the thing is that why is this true? Well, that's because f tilde does not have a zero anymore here on this set, right? Because with potential zeros, I mean, the zeros are among the 0 yi. The zeros of f on the yellow set are among the 0 yi, and they have been taken out here, right? So, but UIs were open, so this is an open set. Union of open sets is open. Now, its complement is closed, and so this is an intersection of two closed sets. So that's actually a closed set, and it's also bounded, of course, so it's a compact set. So if tilde is, it would have been enough to take here those UIs where the corresponding 0 yi lies in the yellow set, right? But that doesn't matter, I can take everything. Since f tilde is positive on this compact set, there is an epsilon between 0 and 1, strictly between 0 and 1, such that f tilde minus epsilon x to the 4 is positive everywhere here. Yeah, because, if this set is empty, then I can take epsilon, anything between 0 and 1 I want. And otherwise, f tilde takes on a minimum and x to the 4 takes on a maximum. Anyway, it's I guess it's anyways less than or equal 1. So I can just take the minimum for epsilon. I could just take a minimum of f tilde on this set if this set is non-empty. Otherwise, anything I like between 0 and 1. Altogether, we have f tilde minus epsilon x to the 4 is positive on this set, right? Because it's also positive on each ui except at 0 yi, right? So it's positive everywhere here. And f tilde minus epsilon x to the 4 is, of course, 0 in these points here. So, yeah, so in particular, it's non-negative everywhere on the yellow side of a cube, right? And then, now I have reduced to that thing, right? In fact, for each side of a cube, for each of 6 sides, I can choose a corresponding epsilon, then I can take the smallest among these 6 epsilons, and yeah, and we have found, yeah, and when I take for the linear form, I take the 4th square root of epsilon times x for the linear form L. So now we need one more lemma. So lemma 756. Suppose f lies on an extreme ray of a cone P of a piece D 4 forms in this ring of polynomials over reals in 3 variables. So here we have a piece D, these are the piece T ternary forms, right? So they build obviously a cone, right, in this R vector space here. Okay, so then there are, and an extreme ray, you know that's a ray 7423b. So let's have a reminder on this. So if you have a K vector space, so K is here the reals in our case, and C is a cone. Then first of all, rays of C are these things here, right? So so the set of all non-negative multiples of fixed non-zero vector in C. And rays that are at the same time faces are called extreme rays of C. That are faces of C are called extreme rays of C. Okay. So suppose F lies on such an extreme ray of a cone P of a PSD for forms. When we are linear independent V1, V2 in R2/3, such f of V1 equals f of V2 is equals 0. So that means, yeah, if you like projective space, that means you could call this also an extremal PSD ternary quartic, has two zeros, has two distinct zeros, has at least two distinct zeros in projective space. Okay. If f were positive definite, so let's prove this. If f were positive definite, then the forms f plus epsilon x⁴ and f minus epsilon x⁴ would be positive semi-definite for some epsilon bigger than 0. In fact, you could take epsilon, for example, as a minimum of f on compact unit sphere of R⁴. That would work because x⁴ is takes on values between 0 and 1 only on the unit sphere. Okay, and because of now I can write f in this form, right? But these two things are also in my cone P, right? And since f lies on an extreme ray, and this extreme ray is a face, right? We know that when f minus epsilon x⁴ and f plus epsilon times x⁴ both have to lie in this face, so on this ray. Okay, and thus, and so you have that f plus epsilon x⁴ is some scalar lambda times f, but this scalar cannot be 1, right? Because otherwise epsilon times x⁴ would be a 0 polynomial. That's not possible. So you can bring this to the other side, and then you see that f is some non-zero multiple, some scalar multiple of f, where the scalar is not 0, is minus epsilon times x⁴. So in particular, f is a scalar times x⁴. And this is a contradiction because because I assumed here that f is positive definite, and a multiple of x⁴ cannot be positive definite. Hence, f has at least one 0, because it is PSD but not PD, not positive definite. So it has at least one 0 in R⁴ without 0, without the origin. After a change of coordinates, we can, without loss of generality, achieve that V1 is the first unit vector, right? The whole statement is invariant under the whole it's easy to see that the whole statement is somehow invariant under invertible coordinate transformations, right? Linear coordinate transformations. Okay, so since 0, 0, since 0, 0 is a local minimizer of the polynomial f of 1 y z, right? Because 1, 0, 0, so f of 1, 0, 0 is 0, right? And f is PSD. So 0, 0 is a local, even a global, in fact, minimizer. We know from analysis that the gradient in this point must vanish. So the gradient of the function that maps yz to this. So and therefore the partial derivative of f with respect to y at the point 1, 0, 0 and the partial derivative with respect to z at 1, 0, 0 must be 0. it follows that there are ABC such that f can be written like this. So f is, and ABC are actually polynomials over y and z. F is a times x squared plus b times x plus c. Okay. And okay, so maybe I should actually say first of all, why is it like this? So you can so f is a homogeneous it's a 4 form, right? It's a 4 form, and so all I'm saying here is that the monomials x to a 4, x to a 3y, and x to a 3z don't appear, right? Because when, you know, in every monomial there is at most the power of x, x appears at most to a power of 2, and then I easily can find this. In fact, I can find, and I should have wrote this right from the start, it follows that there is, or that there are a quadratic form a in the variables y and z, cubic form b in the variables y and z, and quartic form c in the variables y and z, such that this holds, right? Because otherwise, I mean, probably you have understood it anyway in this way, but it's not really written, because otherwise it could happen, right, that, for example, f could be a 0 form and c could be 0, but a could be 1 and b could be minus x or something, right? That's of course not intended. Okay, so so that's how. Sorry, yeah, but I have to argue why these monomials don't appear in f, right? So x to the 4 does not appear because 1, 0, 0. The coefficient of x to the 4 in f is f of 1, 0, 0, which is 0, right? Right. And because v1 is e1, so and f of v1 is 0. So that's okay. So for this monomial, why can this monomial not appear in f? Well, that's because of this condition, right? So because this is exactly the coefficient of this monomial in f, right? Because, you know, if you take this derivative, what monomials of f to survive this derivative? Well, and the subsequent evaluation here. Well, because of evaluation where you set y and z to 0, if you have a monomial, it survives this derivative with the subsequent evaluation only. Well, first of all, it doesn't survive it if y doesn't appear, right? Like for x to a 4. It doesn't survive it if y appears twice, because I said here if y appears to a power of at least 2, because I said after taking the derivative, I said y equal to 0. So it survives only if y appears, if y divides one monomial and y squared doesn't, right? So yes, and so we only and since I'm also evaluating in z equals 0, z shouldn't actually appear in the monomial. So the only monomial that can survive this is this, right? And actually, if you take the derivative of this monomial with respect to y and you evaluate in 1, 0, 0, when you actually get 1. So the coefficient of this monomial in f is actually exactly this. Well, you can see this also from a multivariate Taylor formula or something like this, right? Or it's easy to see. And the coefficient of this monomial in f is this. In a similar way, right? So they are all 0. Good. So now we make a case distinction according to the rank of this quadratic form, right? You can write A as so this is A is a quadratic form, and you can write it as a sum of differences of squares of linearly independent linear forms by 161h, and the number of terms you are using is a unique, and that's the rank 161h. You could also say that's the rank of the representing matrix of this quadratic form, of a symmetric representing matrix of this quadratic form. So it was here, the rank is S plus T here if you write Q as a sum of differences of linearly independent linear forms, right? And that's also the rank of a representing matrix, right? Good. So and what do we have to show? I mean, we have already this V1, which is the first unit vector, and we have to show that there is V2 such that which is not in the linear span of V1, right? So it should be that means not both the second and third coordinate should be 0. So the first coordinate can be anything, but the second and third should not both be 0. So we need a V2 here, such that f of V2 is 0. Okay. So how do we get this? So we make a case distinction by the rank of A. As I said already, I had already reminded you of rank, of a definition of rank. Okay, so now let's do this case distinction. So let us copy this here. Okay. If rank of A is 0, and A is the 0 form, 0 quadratic form, and thus, because f is PSD, you easily see that when B must vanish everywhere when, right? If A is actually not there, f is now for form Bx plus C, and if you plug in, let x be, don't touch on x, but plug in for capital Y as small y in reals, for capital Z, Z in reals. And so this is B of yz times capital X plus C. So that's a linear univariate polynomial, right? It can be PSD only if this vanishes here. That's true for every little y and z. So b of yz is 0 for all yz. And then b must be, of course, the zero polynomial, right? Yeah, if a polynomial vanishes anywhere on Rn, when it is the zero polynomial. And that similar fact would be true for polynomials over infinite fields. And we had a much more general statement here in 223. So if f equals c, right, so c is a quartic form in y and z only. So if this was p positive definite, then again a similar argument as we had already before, as we had here. Here I can do a similar argument for this positive definite form in two variables, right? I take now y to the 4 because variable x is no longer there. It replaces what I did here with x to the 4. That would be positive semi-definite for some epsilon bigger than 0, and it would follow that c plus epsilon y to 4 is in this rate generated by c. And thus c would be a multiple of y to the 4, which is not possible because I said that c, I assumed here that c was positive definite contradiction. So c must have actually a 0, right? So c must have a 0. Yeah, and when we are done, right? Because when we want to show that this v2 here exists, right? And we can take we can choose y's in R2 without 0. So I mean c has a non-trivial 0 and a 0 different from the origin, right? So choose this such that c of yz equals 0. And now, yeah, you can set v2. I mean, it doesn't matter what the first component is now. I just take it to be 0, but it doesn't matter. Set v2 this, and then f of v2 equals c of v2 equals, because I consider c to be a form in two variables, I could write equals c of yz. This is different from 0. Right, so maybe I should write a little more here in the lecture notes still. Okay, so the second case, sorry. Okay. Okay. So the second case is where rank of A is 1. But let me perhaps first add something which I should have told you earlier. Write it here in blue. And in the lecture notes, I will think about what I write exactly in the lecture notes. But it is actually easy to show. It is easy to in blue I said. It is easy to show that A is positive semi-definite, that the quadratic form A is positive semi-definite, using, of course, that F is positive semi-definite. Right? So just fix a little y and a little z, right? And look at, so let me write it here in green. So for a little y and a little z, real numbers, when look at f of look at f of x comma y z, which is a of y z x squared plus b of y z x plus c of y z. And this is a quadratic univariate quadratic polynomial which is non-negative. And since it is non-negative, with a of yz has to be non-negative, of course. And that's true for all y and z. So, okay, so A is positive semi-definite. And if rank of A is 1, when A is a square of a linear form in the variables y and z, so now by a coordinate change with respect to y and z, so I can that doesn't change anything, so my claim is invariant under such a coordinate, such a linear change of coordinates in the yz plane. Yes, because E1 was the first unit vector, right? Okay, so by such a coordinate change, I can make this linear form of which A is the square to be y. Right? So without loss of generality, A is y squared. When B of 0 z equals 0 for all z in R, and hence B of 0 z is 0, right? So it's a univariate polynomial in the variable z. So that means B is, so B depends just, since, that means that B is, that means that in every monomial of B, y variable y divides every monomial of B, right? So B can then be written as yb prime for some B prime, sorry, there must be a prime here, for some B prime, which is a polynomial in x and y again. So it follows that f is of a form x squared y squared, because y squared was with a. So that is, is ax squared, right? When plus bx, which is b prime times y, and plus c. Okay, and that's xy plus b prime half squared plus c minus b prime squared half, right? Okay, so that's kind of a quadratic completion. And when for all y is set in whose for all pairs of real numbers y set where y is non-zero, we find some x in R satisfying xy plus b prime of y z half is 0. So making this 0, right? That's always possible if y is non-zero, right? And from which it follows that c of yz minus b prime of yz squared fourth, right? So I plug in the yz here also, equals f of x yz, which is non-negative, right? And so this is always non-negative for all y and z, with y non-zero, but when by continuity also for all y. And hence this is hence c minus b prime squared fourth is a positive semi-definite quartic. Yes, and exactly. So by the way, I'm really sorry. I think that should be here y comma z, right? Y comma z, I guess. Okay. I'm sorry about that. Yes. So c prime minus c minus b prime squared fourth is in P. Aside from that, we have of course that xy plus b prime half squared is in P, of course, because that's a square of a quadratic form. And since f lies, okay, so I have to be careful. So yes, because b is a cubic form, right? B prime here is a quadratic form, right? So that's okay. Aside from that, we have, of course, xy plus b prime half squared. So since f lies on an extreme ray of a cone P of a PSD four forms, we have that these two polynomials also lie on that extreme ray, because that an extreme ray is a ray of a cone which is a face, and f half is 1/2 times this plus 1/2 times this, right? So since f lies on an extreme ray, f half of course lies also on that extreme ray, and since this is a face, these two polynomials also lie on that extreme ray. Okay, so since f lies on an extreme ray, since f lies on an extreme ray of P, it follows that this lies also in the same extreme ray, which is, and then therefore lies in particular in the linear space generated by f. Actually, it lies, yes. Note also here that f is not 0. I think we use that. It's not a 0 polynomial, because if it were, then the rank of a would be 0. So I can follow that. Now choose choose y and z real numbers arbitrary such that y is non-zero, and then choose an x such that because y is non-zero, we can choose an x such that xy equals minus this, so that we have this, and so this makes now this is now 0 of this quartic here, and since f is a scalar multiple of this, note that f was not a 0 polynomial when it's also 0 of f. Okay, so that was this case, and now the last case is where the rank of a is 2. So since A is positive semi-definite, it's when a sum of two squares of linearly independent linear forms. So by a coordinate change in the YZ plane, these linear forms are without loss of generality Y and Z. So when A is without loss of generality Y squared plus Z squared. So since F is positive semi-definite, also this sixth form here is positive semi-definite. Why is this? Well, take the discriminant, you know what it's discriminant of a quadratic polynomial, of a univariate quadratic polynomial that you know from high school, is if a polynomial is ax squared plus bx plus c with abc real, is b squared minus 4ac, right? And if a polynomial is non-negative everywhere, then this discriminant, so yeah, when there can be no two distinct real roots, right? No two distinct real roots. So this discriminant must be less than or equal 0, right? So so by plugging in, in our case, I mean A, B, C are not real, but after we plug in for y and z, for variables y and z, some values, it is, right? So we see that this is PSD, is a sixth form, it's a sextic form, which is PSD. And we have to show that there is yz in non-zero vector in R2, such that there exists x in R, such that this is true, right? So yes, exactly what we have to show, right? It's just explicitly stated here. Because of A of yz is non-zero, for all yz which are different from 0, you know, because A is now actually, you know, you see it here. This is equivalent to the existence of yz in... Sorry, I mean, here is an x is missing. Sorry, here is an x missing, right? This is equivalent to the existence of yz in R squared without 0. With so yeah, that's again the discriminant thing, right? Having a real root means the discriminant is greater than or equal 0, right? So it's equivalent to the existence of yz such that b squared minus 4ac evaluated in yz is non-negative. That means 4ac minus b squared of yz is equal to 0 because, I mean, you know, this means that 4ac minus b squared evaluated in yz is less than or equal 0, but it's already greater than or equal 0, so it means it is 0, right? So we have to show that there exists yz different from 0 in R squared, such that 4ac minus b squared evaluated in y comma z is 0. So that means we have to show that 4ac minus b squared is not positive definite because it's already positive semi-definite. So aiming for a contradiction, assume that 4ac minus b squared is positive definite. So sorry again here. Is positive definite. When also these two six forms are positive semi-definite, right? So remember that C is a quartic, A is a quadratic form, right, and B is a cubic form. So these are 6 forms. So for each epsilon, real epsilon, this is a 6 form, sextic. Also, these 6 forms are positive semi-definite for some small epsilon, right? Yeah, this is a little exercise, right? That's because, you know, for a y2/4 is bounded, right, on the unit sphere, for example, right? I mean, PSD-ness can be checked just is equivalent for homogeneous, well, for this is a homogeneous polynomial, and PSD-ness means can be checked just, it's just about just amounts to check non-negativity on the sphere because of a homogeneity. So, and this on the compact sphere, right, this is a minimum and a maximum, so that's why there is this epsilon. Easy to show, right? Yeah, yeah, for epsilon, I'm not really sure if that is true what I wrote here. Yeah, that's because yeah, that actually works. Yes, because A is because A is we know already that A is this polynomial. It's 1 on the unit sphere when it actually works like this, like it is written here, I guess. Yes. Yes. Okay. So it follows that f plus minus epsilon y2/4 is in P. Right, because yeah, I mean, so these are PSD, right? And that means you know that this is the negated discriminant. You know, that's the negated discriminant where I consider y and z again as parameters somehow rather than variables of this, right? If I consider this as a polynomial in X, a quadratic polynomial in X, that is parametrized by y and z, right? As I did always now, right? Then you see easily that this is the discriminant of this, right? And so if a univariate polynomial, quadratic polynomial is non-negative, and its discriminant is so this is the negated discriminant, and if a univariate quadratic polynomial is non-negative everywhere, then its discriminant must be less than or equal to 0. So its negated discriminant must be greater than or equal to 0. So that's just this. And then it follows that this is true, and then when f is, you can write f like this, right? And you obtain that f plus and minus epsilon 2/4 are in this ray, in this extremal ray, which is a face, right? And you know, here we use actually again that f is not a 0 polynomial, right? Because A is of rank 2. Otherwise, this would be, if f were a 0 polynomial, when this would be just a singleton set and not the ray, the extremal ray on which f lies, right? By hypothesis. So we obtain f plus epsilon y to the 4 is here, and thus, you know, f plus epsilon y to the 4 is a scalar times f. This scalar cannot be 1, obviously, and then, you know, you get that f is a multiple of y to the 4, a scalar multiple of y to the 4. Yes, and that's not possible because when the rank, for example, here would not be 2, it would actually be 0. Okay, so this was a bit of a technical proof. And now I think we have almost all together. We need another lemma, but this is not a big deal. So let Dn be non-negative integers and let V be the R vector space of all 2D forms in variables x1 up to xn, and let P be the cone of all positive semi-definite 2D forms in the same variables, right? Then P is a closed cone with compact convex base, right? So remember what was a base, 7, 4, 23, C. Right, so if you have a cone, when a subset not containing the origin is called a base of it, if every ray of C hits the set B in exactly one point, right? Rays of C are the subsets of C of this form where X is a non-zero vector. Okay. And you have a compact convex base. Let's prove it. So as an first, why is P closed? Well, that's easy. You know, the set of all in this finite dimensional R vector space, right? Every linear form on this finite dimensional R vector space, as you know, is continuous. I mean, you have exactly one vector space topology here. And because it's a finite dimensional real vector space, and that's the topology we are speaking about. And it could also be defined as the initial topology with respect to all linear forms, right? And one of these linear forms is the evaluation in X for a fixed X in R to the n, right? So these linear forms are all continuous, and therefore I could call it the evaluation in X, right? And therefore the pre-image of a closed subset of non-negative numbers in the reals is of course closed, right? Pre-images of closed sets under continuous functions are closed. And but this here is exactly this here, right? And now if I intersect an arbitrary number of closed sets, I get a closed set again, right? And so P is this intersection, and that's closed. Next, so why do I have a compact convex base? Well, this will be an interesting argument. So one way of doing it is first to define a norm as follows. So a norm on this finite dimensional real vector space of all 2D forms in n variables, right? So I define the norm of such a 2D form as the sum from x1 from minus t to d, etc., up to xn from minus t to d. So it's a sum with how many terms? It's a sum, well, one of these sums here, each of these sums has 2d plus 1 terms. So in total I have 2d plus 1 to the n terms in this sum. Right, and when I sum here over the absolute value of p evaluated in x1 up to xn, right? So what happens? So if n is 2 and d is 3, then I have here a grid like this. Right, and I evaluate p in each of these grid points, and I take the absolute values and I sum it up. And of course this is, of course this satisfies the triangle inequality, and it's homogeneous and it's non-negative. And the only thing that remains to show is that if a norm of, so in order for it to be a norm, is that if the norm is 0, then the polynomial should be 0. Okay, but that's by 2 to 3. So where is 2 to 3? It was this, it was this lemma here. So we take here, for k, we take a field of real numbers. When I have here, I had n variables, and I had here 2D forms, so I can take here, instead of D, I can take 2D. And then if I have here subsets of cardinality 2D plus 1, right? So instead, take 2D instead of D. And in fact, I can take, a set of numbers. I will just take the set of numbers from minus D up to D, right? So when the cardinality isn't, and this for every I. So when the cardinality is 2D plus 1, I take 2D instead of T. And when if f is null, if f is 0, in our case that is this grid, when f is the 0 polynomial, right? So if a norm of p is 0, then that means p is 0 on this grid, p vanishes on this grid, and then the lemma says p is the 0 polynomial. Okay, so I take this defines a norm, and when I define my base to be a set of all p in p with norm 1, right? That looks, that's a unit sphere in some sense, right? A unit sphere with respect to this norm. But this norm is built in a way such that when I intersect the cone P with this unit sphere, that when it looks actually, when I get actually a flat, a convex intersection, right? So now you have here a cone, and then, this unit sphere really intersects the cone in a convex set, right? Whereas, of course, this unit sphere otherwise might look more complicated, right? I don't know how to draw it. Anyway, so, and why is this? Because the norm, so in the norm I have here the absolute value, right? So actually one would think one has to write here the absolute value, right? Actually, I guess this is a typo, that should really be P and P, sorry for that. So one would think that I should take here the absolute value. That's of course true, but if I'm here just looking at P's in P, at positive semi-definite forms, P consists of positive semi-definite forms, when this here is automatically always non-negative, right? So I can forget here about this. But now you see that, the set of all P in V, if you look at the set of all P in V, such that you have this, right? When this is actually an affine subspace, that's actually an affine subspace, as you see immediately, right? And so an affine subspace is of course convex. And now if you intersect this with P, with a convex, with a cone P, it's itself a convex set, of course, then you get the convex set, right? So B is convex, right? B is convex. And why is P a base? So yeah, that's very easy to see. So if you have an element in the cone P which is not a zero polynomial, then there is of course a unique positive scalar such that if you multiply it with a scalar, you get this expression to be 1, right? Very, very easy to see. Yes. I think that uses again 2 to 3, right? Well, since you know already, yeah, I mean, you can also see it from the fact that this is a norm. So this is a compact convex space, right? It's convex. It's compact, right? You see this. It's bounded with respect to a norm on a finite dimensional real vector space, and it's closed. Yeah, that's it. So it's a compact convex space. So now we can more or less start with harvest. So with the following lemma. So remember that in this chapter we want to prove that every positive semi-definite ternary quartic over a real closed field that is positive semi-definite is a sum of squares. Hilbert actually proved in 1888 that it is even a sum of 3 squares. We don't prove this in the general case. So the overall idea was to prove it using results of convexity, and therefore we worked over real numbers actually. And then we will later go from, with Tarski's principle, we will go from the real numbers to a real closed field. So for the moment we stay with real numbers. And the second main idea of a proof is that we use the conic version of Minkowski's theorem. Namely, we first treat ternary quartics that are on the extreme ray of the positive semi-definite ternary quartics. And yes, so and they are, so for them we will now prove that they are sums of squares of quadratic forms. And actually, since they are on an extreme ray, then it's even a square of a quadratic form, right? So the proof is, so it is enough to show that f is a sum of squares of quadratic forms. For if f is a sum of quadratic forms, it suffices to treat the case where f is not a zero polynomial, so let's say it's non-zero here. If f is a sum of squares of quadratic forms, then you know it's easy, you can write f as 1/2 times this, plus 1/2 times the other things. So actually note that m was greater than or equal 1 because this was not a zero polynomial here. And yes, and of course this is again in my cone P of positive semi-definite ternary quartics, this also of course. And but f was an element of this extreme ray, And yeah, so f and yeah, so f is an element of array. This array actually is, of course, this one, right? It's the set of non-negative scalar multiples of f. You know, a priori, the array is something like this, with G non-zero and G in P, but when if f is in there, then and if f is not zero, which was the case here, then it follows, of course, that that these rays are the same here, right? So you can do this easily. So therefore, this set here, this ray is a phase of a P, P, and since f is the midpoint of a line segment that is entirely in P, of a non-trivial line segment, then this must also lie on the face, and this actually also, but the first one is enough. So Q1 squared is in the same face, and okay. And then, you know, you see that you can write f as a sum of a square of a linear form. You see it easily, right? So if there is a linear form, okay, so so it's enough to show that f is a sum of squares of quadratic forms. So then let's first treat the case where we have the case where there exists a linear form L, non-zero linear form, such that f minus L to the 4 is positive semi-definite. If we have this, then, you know, it's again easy. It's exactly like, it's exactly the same argument, again using that this extreme array is a face. We get that L to the 4 is a non-negative multiple of f, right? Just as we got here Q1 squared is a negative multiple of f. And therefore, you know, since L is not the zero polynomial and L to the 4 is therefore not the zero polynomial, I see that f equals some non-zero constant in the real numbers times L squared squared. Okay, it's easy to see. And so f is a square, actually of a square of a linear form, but in particular it's a square of a quadratic form, and we are done. From now on, therefore, suppose that such a linear form does not exist, right? Such an L. Then I use lemma 755 and 756, and I claim that it follows that f is a sum of 3 squares of quadratic forms. And when I'm done, of course, right? So why do these two lemmata now imply that f is a sum of 3 squares? So let's look at 755 and 756. So 755 perhaps first, right? So the conclusion of 755 was that there exists such a linear form L, such that non-zero linear form L, such that f minus L to the 4 is positive semi-definite. But we are now in the case where this is not the case, right? So that means the hypotheses of lemma 755 are not met, right? Now, what are the hypotheses? Well, f is a PSD4 form. That's something we have. That is also part of our hypothesis. So something else has to be has to be not satisfied, right? So what about two linear independent zeros? Maybe f does not have two linear independent zeros. Well, lemma 756 says it has, actually, right? Okay, we come back to this in a second. And therefore, the only thing that can be violated is that f is not the sum of three squares of quadratic forms. So this is violated. So f is the sum of three squares of quadratic forms, right? And therefore, it's the sum of quadratic forms. And therefore, you know, in the end, it's actually a square of a quadratic form because I was on this extreme ray. Now, lemma 755. So a key is lemma 755. And we also use lemma 756. That says that the reason why the hypotheses of lemma 755 are not satisfied cannot be that there are not two linear independent zeros of f. Namely, 756 says there are, because f lies on an extreme ray. Good, okay. Sorry, here we are here. Okay, good. So that's it. So that's already a lot, right? This lemma is already very, very strong and is close to what we want to prove. Now we can go to a final result. Let R be a real closed field and F ternary quartic when the following are equivalent. F is positive semi-definite, F is a sum of squares and of polynomials, and F is a sum of squares of quadratic forms. So C to B to A are trivial. For A to C, I claim that this, so first let's treat the case where the real closed field are the real numbers. For this case, it follows from what we have just proved, you know, because every, from what we have just proved, it follows that elements that lie on an polynomials that lie on an extreme ray of a cone of positive semi-definite ternary quartics are squares of quadratic forms. But any other positive semi-definite ternary quartic is actually a sum of such polynomials that lie on an extreme ray, right? Why? That follows from the conic version of Minkowski's theorem, right? So let's see, 7425. It's here. Every convex cone with compact convex base in a finite dimensional real vector space is the sum of its extreme rays, right? So that means every element of this cone is a sum of elements that lie on extreme rays of it. A finite sum, right? So, good. So, why do we have a cone with compact? Actually, I don't need convex here. I'm sorry about that, because by definition, cone was always convex. Okay. Why do we have a compact convex base? Why do we have a compact convex base? Well, that was also this lemma here, right? So we also use 757, right? So it follows from maybe I should say here N757. 757. Okay, so now how do we get, so now we have already everything for a case where a real closed field is the field of real numbers, but how do we get to a general case? Well, that's an application of Tosca's principle, so that's something very similar to what we did several times already in this series of lectures. So let's take R is the class of all real closed fields. And if you don't like classes, then I've told you several times how you can get around this. And then we take S. S should be the class of all real closed fields R, such that you know, for all four forms in three variables, not over the reals, but over the real closed field. If F is PSD, just write just like this. When F is a sum of squares of quadratic forms, right? And actually, let me write it like this: there exists Q1 up to Qn such that F equals Q1 squared. Okay, so I have to say quadratic forms. So two forms. Such that F equals the sum from I equal 1 to n Qi squared. Right, so let me make this parenthesis red. So I close it here, right? The red one, and then that's the end of the definition of this class, right? And so what is the problem with this definition of S? Well, the problem is with capital N here, right? What should it be, right? So do I want to say there is such a capital N, right? So do I want to say there exists a non-negative integer N such that this is true? But that will be a problem. So the basic strategy is, of course, that I want to show that curly S is a zero-ary Q semi-algebraic class, right? A zero-ary semi-algebraic class. So semi-algebraic class. And if I can show this, when I'm done, because there are only two such zero-ary semi-algebraic classes, namely curly R itself and the empty class, right? But I know that R, so I have already shown that the real numbers are an element of it, right? Real numbers are in there. So then it must be everything. So when I conclude S equals R, S equals curly R. So, so if I want to show that S is a zero-ary semi-algebraic class, I use, of course, my elimination of quantifiers, right? But elimination of real quantifiers. But with that, I cannot eliminate the quantifier like this, right? So it would be better if I have here an n specific n, like n equal, I don't know, 5 or 10 or 20, right? So let's do away with this quantifier here. So, but if you want to show that the real numbers are in there, then yeah, then we would need here some bound. I mean, for the real numbers, we know that every PST ternary quartic is a sum of squares, but we would need some bound. We would have to know that it's a sum of at most that and that many squares, right? 5 or 10 or 17 or whatever. So do we have such a bound? So that's now, it all boils down to that question. Do we have such a bound? And the answer is yes. We have it, and we can even give several reasons why we have it. And one reason is the Gram matrix method. But first, let's really see that when we are done, right? So how would we then prove that this curly S is a zero-ary semi-algebraic class? Well, we would eliminate quantifiers, right? So first, yeah. So this is, here I quantify over polynomials, but this is a polynomials in a fixed number of variables, namely 3, of a fixed degree, namely 4, right? And so I can just write this, I could just speak about this, this universal quantifier over polynomials can be modeled by, you know, how many monomials of degree 4 in 3 variables do I have? I don't even know, I don't want to count, but I have a certain number, and I could just write this number of quantifiers over real over elements of this real closed field R, right? So in this way, and quantifiers over R, finitely many quantifiers over R, I can eliminate, right? And yeah, and here this is anyway quantifiers over R, free universal quantifiers over elements from R. You know, this is a polynomial inequality in the coefficients of f and in x, y, z, right? So that's okay. And this is just implication, you know, that's something I can express by complements, finite intersections, finite unions. And here again, I have to speak about these polynomials. I can do this by speaking about their coefficients, since the number of variables and the degree is fixed. That's no problem. The only problem, as I said, is the number of quadratic forms here. But if I have a bound on this, then it's okay. And this is just a polynomial equation in the coefficients of f and the coefficients of a qi. Right? So you know if n is fixed now. So yeah, now we have to speak about this capital N. One way of proving this bound capital N is using the Gram matrix method 261. Okay, so So if you look at this here, right? So, you know, I want a bound for the number of squares I need in a sum of squares representation. And that's exactly what is given here. Namely, I have here that being a sum of squares is equivalent to being a sum of m squares. Okay? So that's, and what is m here? Well, what can I take for m? Well, I can take 1/2 a Newton polytope of f intersected with, a Newton polytope of f is of course contained in, you know, in our case f is a homogeneous, is a 4 form, right? So the Newton polytope of a 4 form is of course contained in the Newton polytope of a 4 form is of course contained in the set of in the convex hull of 4 form in 3 variables actually. 4 0 0 0 0 4 0 and 0 0 4. Right? Easy to see. And so I have just to take 1/2 of it. So 1/2 of this Newton polytope is contained in the convex hull of 2 0 0 0 2 0 and 0 0 2. So now I have just to count how many tuples with with integer coefficients are in there. So where is, let's see, so where is 2 0 0, there is 1 1 0 1 0 1, and there is 0 2 0 0 1 1 and 0 0 2. These are all right. These are 6. These are 6, and yeah, and so I get that f is a sum of 6 squares, right? Of 6 squares. And okay, so as I said, by the way, Hilbert in 1898 actually proved sum of 3 squares, but we don't prove this here. This proof is quite a little bit more involved than what we do here. Okay, so yeah, so and that now, if you have, so you could actually here take 6, right? Here I could take 6. And another way of finding such a bound n here would be as follows, and that's written here. So 7 4 20. I could use 7 4 20. So namely, the idea is that here in 7 4 20, it's not clear what is actually the connection at first. So of course we take here for k less than or equal, we take just the real numbers, and when we take here for the vector space, we take the vector space of ternary quartics. Okay, that's a finite dimensional vector space. How many elements? So let's see how many monomials can a ternary quartic have. X to the 3, x squared y. Oh, sorry, ternary quartic. Sorry. It's degrees 4. X to the 4, x to the 3 y, x to x to the 3 y squared, x squared y squared, x y to the 3, and y to the 4. That's all the monomials that involve only x and y. Now those which involve also a set. So let's say which involve set once. So I have x to the 3 set, x squared y set, x y squared set, and y to the 3 set. Now those which involve a set squared. So when we have here x squared, xy, z squared, and y squared, z squared, and those which involve z to the 3 and z2, and the last one is z to the 4, right? So let's count. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right? So it's a 15-dimensional vector space. And now if you have a ternary quartic, which is a sum of squares, right? So you have of quadratic forms, finitely many, right? Let's say from 170, for example, okay? Right? Okay, when I set E to be with Z, right? The set of summands. Now, if E, that's a finite set, and if the problem is it might not generate V, right? But if it generates V, in case it generates V, then I know that E contains a basis of V, right? So that means it contains a 15 subset of cardinality 15, right? That generates a cone containing X, but that means I know that F is a non-negative linear combination of 15 of these qi squared, right? And therefore it's a sum of 15 squares, right? So there is only this little problem. Okay, so sorry. If condition A occurs, so if my set E generates V, right? That might be still something we have to speak about. But it should generate V. So let's see. Yeah. What do we do about this? If it generates V, when either A occurs, right? Exactly one of the following occurs. A occurs, and when we are done, right? When we have bound 15, and or something else occurs, but with something else, of course, is not possible, right? Because our polynomial is a sum of elements of E, and therefore it's not possible that there is a linear form mapping E to the non-negative real numbers and our polynomial to the negative ones, right? So that means the only problem is here, right? And if we can solve this problem, when we get here a much worse bound, namely 15 instead of 6, right? But that's also good enough for what we want to do here. Okay. Anyway, Hilbert proved still much better bound of 3, which we don't use here and we don't prove here. So what's the problem with this? If E is a finite set that generates V. So how can I resolve this problem here? But that's very easy. You just add some squares. You add some squares that generate V as a vector space, right? So you can just, Q1 squared up to Q15 15 squared. Why are there 15 squares that generate V as a vector space? Well, that's because, you know, the vector space is, if P is the, the vector space is the span of, is the linear span of all squares actually, of quadratic forms, right? Right. So why is this? Why is every ternary quadratic a linear combination of squares of quadratic forms? Well, that's every first of all, V is certainly generated by the products of quadratic forms like P times Q, where P and Q are quadratic forms. PQ quadratic forms. Well, that's really easy because every monomial, because V is generated by the monomials, and every monomial of degree 4 is a product of two monomials of degree 2, right? And a monomial of degree 2 is a quadratic form, okay? So that's really easy, and from this, this follows with a little trick, you know, we have seen similar tricks many times. So P plus Q half squared minus P minus Q half squared is actually, maybe I have to take the square root of 2 here. Okay, that's actually P squared, yeah, that's actually, okay, that's, let me see, so that's actually P times Q, yeah, that's P times Q. Okay, no, sorry, that's 2 times P times Q, right? So, but that shows that P times Q is a difference of 2 squares, and so from this we get then this thing here, and when we take a generating system of V, finite set of squares that generates V, yeah, and we can actually take 15, right? Because the dimension is 15. We can, yeah, and when we take here for E this set instead of just a blue set, we take now this set here. And then that's okay when we get the bound 185 instead of 100. So when we get that F is a sum of 185 squares, and when we get that it is a sum of 15 squares by using A here. Okay, so so you've seen many ways of doing this, right? And there is, maybe I should also say there would be another way of using the Gram matrix method to do this thing, right? Because if I want to express that F is a sum of squares of quadratic forms, I could also just say there is a PSD Gram matrix for it, right? And so that would be another way of solving the whole problem that I want to be able to apply quantifier elimination. So I could say that there is PSD gram matrix where exists a symmetric matrix. What do we need? Yeah, the dimension of vector space of ternary quotics was 15. So let's just take all homogeneous monomials of degree 4, right, in the gram matrix method. And so we can do with 15 by 15 matrix G. If and only if there exists a G 15 by symmetric 15 by 15 matrix such that for all V in R2 of 15, V transpose GV is greater than or equal 0. So that means it's PSD. And F equals, now I take here all monomials of degree 4 in 3 variables. Blah, 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 blah. G, x to the 4, blah, 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 blah. Right? And when I close this here, and this, and this, and this. I hope I did it right somehow. Right, so that would be another way of doing it, right? So here now I have just quantifiers. So I said already how to deal with these quantifiers. So here quantifying over this matrix, well, you can do it by, you know how many different entries such a 15 by 15 matrix can have. At most, like it's roughly 15 squared half. And so you take that many number of existential quantifiers. Here these are just 15 universal quantifiers, our elements of R. Sorry, I should have taken R, not the real numbers. And this is a polynomial identity. How do you model this? Well, we have seen that many times. Just take comparison of coefficients on both sides, right? And then you have some polynomial equations in the coefficients of f and the entries of g, right? Okay, so you could also use this gram matrix method 261 instead of using the equivalence of A and C. So let's look at it again. Instead of using the equivalence of A and C that we used before, we could also use the equivalence of B and C. That would be another way of doing it, right? Okay. Anyway, you're using the gram matrix method or with our result 7420. One sees that the class of Fourier crossed fields R, for which A implies C holds for all four forms F. Maybe I should actually say here 4 forms or something. Is semi-algebraic, right? And then by 185, every real closed field belongs to its class. Because we only zero Airy semi-algebraic classes are whole curly R or the empty class. In short, the statement follows thus from the case where R are the reals by the Tarski principle, right? Okay, good. So that's now the main result. So now a corollary. So this was about homogeneous polynomials of degree 4 in 3 variables. If we dehomogenize such a polynomial, when we get polynomial, an ordinary polynomial of degree at most 4 in two variables, right? So let's try to translate this result from a homogeneous setting into a non-homogeneous setting when we get this corollary 7, 5, 10. So let R be a real closed field, f a polynomial in two variables of degree at most 4, when f is non-negative on R2, right? That replaces the PSD-ness, if and only if f is a sum of squares, right? I could also write if and only if f is a sum of squares of quadratic polynomials, but we know that anyway already. So we know that, yeah, that's automatic if it is a sum of squares when it's a sum of squares of quadratic polynomials. So one direction is of course trivial from right to left. For the other direction, suppose f is non-negative on R2. Of course, we have to reduce everything now to a homogeneous case. So, well, there is this little... So if f is actually a constant polynomial, then we are certainly done. So forget about that case. So without loss of generality, f is not constant. When such a sum of squares, you must have even degrees. So the degree can only be 2 or 4. Because we said the degree should be at most 4 by 2 to 4b. Yeah. Right. So that's here. When if I have such a representation over a real field, I said it already some time ago. When if a degree is 2D, when the degree is even, and actually the maximum degree of the summons is D. Of VPIs here, sorry, of VPIs, of the things under the squares is D. Okay. So if the degree of f is 2, the claim follows from 2, 3, 5. Well, when f is, a quadratic polynomial, and in 2, 3, 5, we proved that non-negative quadratic polynomials, let's see, are sums of squares. That worked even over Euclidean fields, right? Okay. So it's okay. So that was also easy. Now, suppose therefore that the degree is 4. Then I look at the homogenization, right, of f with respect to z, right? And this homogenization is positive semi-definite by 2 to 6a. Yeah, because the homogenization is non-negative if and only if the original polynomial is non-negative. That works over any ordered field, in fact. So, yeah, also note that this was the definition of a homogenization here in 224. So if star is PSD, but if star is a ternary quartic, right? So I homogenize with respect to a variable set. So I have now a polynomial in 3 variables, actually, of ternary quartic. So now 759 yields that f star is a sum of squares, right? And by dehomogenization, that means I just plug in 1 for the new variable. It follows that f is a sum of squares, right? Note if you homogenize and when you dehomogenize, you get always back the original polynomial, right? Okay, and note also that dehomogenization, since it's just replacing a variable by a number, it is actually a ring homomorphism, and therefore it preserves sums of squares. Every ring homomorphism maps a sum of squares, of course, to a sum of squares. So we are done with this. So, okay, so one remark. A posteriori, we see now that in the situation of the lemma 756, so let's look at 756. Okay, so it was lemma 756. So what was the situation there? So suppose f lies on an extreme ray of a cone P of a PSD ternary quartic. In this situation we showed that there are linear independent V1, V2 in R2 of 3 such that f of V1 equals f of V2 equals 0. I could say that there are two distinct points in the projective space where f is 0. So now we can show more. We can show that there are infinitely many pairwise, in fact I meant here pairwise linear independent zeros of f. Or you could say infinitely many pairwise distinct zeros in the projective space, if you like projective space. Okay, zeros of f. So we are much more. This follows from 758. So we don't need this, by the way, but just for increasing our understanding. So this follows from lemma 758. Because if something lies on an extreme ray, we said of a cone of PSD forms when ternary quartic PSD forms when f is a square of a quadratic form, right? So in fact, it's a square of a quadratic form. Now let's see. So the zeros are then just the zeros of this quadratic form. Now here I don't understand anymore what I meant. I probably think that the argument is not quite right here. So please delete this here. I will correct it in the lecture notes. So in fact, if f, so this follows from 758. Yes, that means that every element that lies on an extreme ray is a square of a quadratic form. And actually I will also need 756, right? So I will also use and 756. So indeed, if so by 758 we know that f is a square of a quadratic form. And without loss of generality, we can say that this quadratic form should have non-negative signature, otherwise replace q by minus q, right? And hence the signature of q is 3 to 1 or 0, right? 3 to 1 or 0 is 0, 1, 2, or 3. Okay. If a signature of Q is free, then Q and thus F is positive definite, which it is not by 756, right? Yes. Yeah, I mean, maybe I should actually argue from here on in another way. So if signature of Q is 0, when Q is 0, and F is 0, and we are done. Because when, just take, there are many possibilities now. Take e.g. The zeros one y 0 for y in R. Each two of these points are linearly independent, right? It's easy to see. Okay, because if lambda, okay, take such a matrix, take a y1 and a y2, which are distinct, right? And take this matrix, so you have to show that the rank of this matrix is 2, but you can do some row reduction here, so you get here 0. If you subtract the first row from the second, right, you get this. So now this is non-zero, right? And yeah, so that was really easy. So if a signature of Q is 1, then after a linear change of coordinates, which I can do without loss of generality, right? Q, when without loss of generality, Q is x1 or is x squared. And we are again done when we take e.g. The zeros zero 1 y for epsilon for okay, maybe I should write 0 1 z, but it's just up to permutation. It's when exactly the same thing I've taken just before. 0 1 z for z in R arbitrary. So if a signature of Q is okay, when there are actually two cases for where signature of Q is 1. So first case is this, Q is x squared, and the second is or Q is x squared plus y squared minus z squared after a linear change of coordinates, right? And then in this case we can take here take x comma 1 comma square root of x squared plus 1, and these vectors are pairwise linear. So for x in R, and these vectors are pairwise linearly independent, because even if I just take the corresponding vectors with the first two components, right? I just delete the last component, even when they are linearly independent, and that's exactly the same thing as for the same reason as these were linearly independent, right? So here we have two cases, yeah. So if a signature of Q is 1, then we have two cases. If a signature of Q is 2, then 2, yes, sir. Okay. Then one possibility is so it could be 3 minus 1 is not possible, right? So there are only 3 linearly independent linear forms at most. It cannot be 4 because I have only 3 variables. So it could be that Q is a sum of 2 squares. That's actually the only sum of 2 squares of linearly independent linear forms. That's actually the only possibility, right? When without loss of generality, Q is x squared plus y squared. But that, when the only zeros of Q and therefore of F would be the triplet 0, 0, comma set for arbitrary set, but that would contradict 756, because then we wouldn't have 2 linearly independent zeros, right? Which contradicts, however, 756. And if signature of Q is 3, the same thing, then without loss of generality, Q is x squared plus y squared plus z squared, which contradicts even more. That contradicts even the existence of 1 non-zero zero. It's even more. 756. Okay, so I have to write this in a much better way in the lecture notes, okay? Yeah, and the final remark, we will neither use nor prove the following. So I said it several times already, in 1888, Hilbert showed the strengthening of 759, namely he showed even that we have here f is a sum of 3 squares of quadratic forms as another equivalent condition. Well, remember that we showed in several cases, in several maybe very special cases, we showed that also in 752, 753, 754, this was the series of our 4 lemmata. That was this series of 3 similar lemmata, right, where we had always some very special hypotheses which say something about zeros of f and directional derivatives at zeros of f. And then there is, there was also 755, by the way, which said that if something is not a sum of three squares when something happens, so that's also a little bit in the direction of Hilbert's sharpening. So, but it doesn't give it, right? So at least we don't see. So if we have something which is PSD, but not the sum of three squares when this has to happen, so f minus L to the 4, where L is a non-zero linear form, is still PSD. Yeah, that. So we dealt quite a little bit with this condition being a sum of three squares, but I don't think we got really very close to the original Hilbert's theorem. Now there are several proofs nowadays for Hilbert's theorem, but if you look for those which are easy to understand for master students, then there is this one, a very long and tedious elementary proof for this has been given by Scheiderer and Pfister in 2012. Well, second remark, you could also, maybe you would also like to think about when is a PSD ternary quartic with rational coefficients a sum of squares of quadratic forms with rational coefficients, right? That's an interesting question. Is that always the case, right? In fact, Scheiderer showed in 2016 that this is not always the case. So he gave this ternary quartic, which can be checked to be PSD. So we will not prove it, but we will also not use it. That is not a sum of squares of polynomials with rational coefficients. And yeah, in the same year, Henrion, Naldi, and Safaeldin gave an elementary proof for this non-existence of rational representation. Okay, so in fact, until Scheiderer found such an example, it was even not known whether every real polynomial, real globally non-negative polynomial, which is with rational coefficients, is a sum of squares of polynomials with rational coefficients. That was not known, and people have thought about this for some time until my colleague Klaus Scheiderer showed this to be not the case in 2016, and he could do it even with a ternary quartic. Okay, so we end with this section, which was, I think, very useful, not only because we proved some theorem concerning non-negativity and sums of squares, but also because we really used many notions and many results we had proven for convex sets, which we will have to use again later on. Okay, thank you very much for listening, and next time we start with a new chapter, namely a chapter on non-negative polynomials with zeros. Thank you, goodbye.